All right. Thank you. Hello, everyone. How are you all doing? Hello, guys. How are you all doing? Well, let me see some response from you guys. Well, I'm hoping that you all are doing great and you all must be busy in preparing all those competitive examination like one NEET is approaching soon this weekend and also the JEE advanced examination, right everyone? How's it going, guys? How's it going? Okay. Excellent. Well, guys, so small introduction before we actually start. This is Sagar Darvi, your chemistry teacher, and I welcome you all to a marathon session, which is a complete organic chemistry in one shot at Physics Wallah. Well, guys, before we actually start with our today's session, let me just brief you about how exactly this session flow would be and what all are you going to learn. So, guys, you all are aware that 5 to 6 hours isn't really enough to complete the entire organic chemistry. However, we are making sure that all the important concepts and some of the important chapters have been covered in this session. So the flow of session would be we'll be learning some important concept from some of the important chapters. In between, we'll also make sure that we are solving some of the previous year questions so that you get an idea of how exactly the concept have been molded into some of the questions as an application of that particular concept. So guys, are we all ready to get started? Everyone? Yes, let me just see. All right. Yes, of course, everyone, we will be covering some part of theory and there are going to be some question as well. So it's going to be a mix of the question as well as concept. You will see all varieties of questions over. You will see some question have been asked from JEE Main. There will be some question from JEE Advanced as well and some question from the NEET as well. So guys, let's get started. Well, before we start, let me just brief you about what exactly are we going to learn. So this is our today's learning objective. As you all can see on your screen, we'll be learning about general organic chemistry. That is a topic that we are covering. So all the important electronic effects and its application followed by aromaticity is what we are going to see in this general organic chemistry. Followed by we'll be also talking about some part of isomerism, including structural as well as stereoisomerism. And then we'll be also talking about comparison of substitution reaction SN1 versus SN2, as well as we'll be discussing elimination reaction as well. So that is what all about the reaction mechanism we'll be discussing, followed by some important reaction and the problem solving with respect to, as I said, previous year questions we will be discussing from hydrocarbon and alkyl halide, followed by alcohols and ethers, and then at the end, how can we forget the most important chapter, that is aldehydes and ketones. So guys, this is all what we are going to learn in our today's class as far as our complete organic chemistry in one shot is concerned. So guys, I want you all to hold on to your seat and make sure that you guys are paying attention to everything that we are learning. I'm sure that our today's class is going to be a lot helpful to you all. So guys, let us begin without wasting even single minute now. Well, so to begin with, we are starting with a general organic chemistry. Guys, when we talk about organic chemistry, we always discuss about reaction. The first impression of organic chemistry is it's all about reactions. Of course it is, but there are many other concepts also involved behind this reaction. However, if we talk simply about what reaction is, suppose if I ask this question to any layman, or let's say to you, if I ask you what is reaction, probably you'll end up answering, sir, reaction is nothing but conversion of reactants into products, which is absolutely correct. But if we have to put this definition on a paper in the form of chemical equation, how will we do that? Well, so I will say a simple reaction can be put in the form of chemical equation in the form of A plus B giving you C plus D. Isn't it, everyone? Where in general we say that A and B are nothing but reactants and C and D, what we are getting are the products. Of course, out of C and D, anything that is our area of interest, if we get the desired outcome, we call it as product, and along with that, whatever else we get, we call it as byproduct. So in simple terms, we can say it's a conversion of reactants, that is A and B, into products, let's say C and D. Now, when you talk about reactants A and B, we further classify these reactants into two categories, which is substrate and reagents. Now, what is substrate and reagent? Guys, let's say there is a reactant called B, which has a tendency to attack at A. So the one who attacks, that reactant who attacks, is what you call it as reagent. So I will say one of the reactant that we have got here is a reagent, and the reactant which undergoes attack from a reagent is what we call it as substrate. And if you get the desired outcome, you call it as a product. Meaning, when I have to express a reaction in the form of chemical equation, I would say substrate is attacked by the reagent, and if we get the desired outcome, you call it as a product. That's how you can simply put the reaction in the form of chemical equation. Everyone, are you all understanding? Are we getting? Am I audible, everyone? Can you see me? Can you hear me properly? All right, excellent. I can see so many enthusiastic students here. Good to see you guys here. All right, guys. Now let's take it further. So when we say reagent is that reactant which has a tendency to attack on a substrate, so we also know that reagents are of two types, electron rich and electron deficient. Electron rich reagent we call it as nucleophile, and electron deficient reagent is what you call it as electrophile. Now think this way, whatever kind of reagent we have here, that reagent is going to attack on a substrate. So let us assume that the reagent is electron rich. If reagent is electron rich, then naturally it will have a tendency to attack at the electron deficient center in a substrate, which means for a reagent to be able to attack at a substrate, there has to be opposite center. If reagent is electron rich, substrate must have the deficient center. If reagent is electron deficient, then the substrate must have electron rich center. So then question arises, from where do we get those opposite center for the reagent to attack on it? So that opposite center in a substrate is generally, again not always, is generally developed as a result of the movement of electron in a substrate. So the movement of electron in a substrate happens due to the approach of reagent. Again, it's not necessary that the movement of electron in a substrate will always occur due to approach of reagent. Sometimes it can happen within itself due to the different electronegativities of atom. But when the reagent is approaching the substrate, that opposite center will be developed as a result of movement of electron always. That movement of electron results in several electronic effects depending upon what kind of electronic movement is taking place. If the movement of electron takes place with respect to sigma electron cloud, or you can say sigma bond pair, the type of electronic effect that appears, we call it as inductive effect. If the movement of electron in a substrate takes place as a result of complete transfer of pi electrons, then we get another type of electronic effect called as electromeric effect. Whereas if the lone pair of electron along with the pi bond, if shows movement in a substrate, then the type of electronic effect that takes place, we call it as resonance effect, or sometimes also referred as mesomeric effect. We are not getting into the details of differences of two. As of now, we are talking about resonance or mesomeric effect as one and the same thing. And if the sigma bond pair delocalizes or if shows movement, then the effect that we observe is hyperconjugation effect. However, difference between the inductive and hyperconjugation effect is, in case of inductive effect, it is just a shift of sigma electron pair, whereas in case of the hyperconjugation effect, it's a complete delocalization of sigma electron pair. So guys, that's how we are going to proceed with our general organic chemistry, learning these 4 important electronic effects: inductive, electromeric, resonance, and hyperconjugation effect. Let me tell you, whether you're preparing for NEET or whether you're preparing for JEE Advanced, the remaining 2 examinations which are coming soon, guys, you all will need help of this electronic effect. You will see several questions have been asked in the previous year question papers in all this kind of examination. So make sure that you guys are understanding this, whatever we are learning under this. So we'll first be taking concepts of this. We'll discuss about some important theories, and then straight away we'll enter into the problem solving. That is the application of this electronic effects. So guys, to begin with, let us start with inductive effect. Well, to understand the inductive effect, let us consider we have got a covalent molecule where atom A is connected to atom B through a sigma covalent bond. So this is the sigma covalent bond between A and B, such that electronegativity of atom B is more than electronegativity of atom A. If atom B is more electronegative than atom A, then we say this B will pull the bonding pair of electron towards itself. So the electron density in the form of sigma bond pair will be shifted in favor of B, making this atom B partially electron rich and leaving atom A partially deficient. Now guys, you can see here, due to differing electronegativities of 2 atoms, one of the atom has become partially electron rich and the other became partially deficient, meaning this development of partial but opposite charges across the sigma covalent bond, we call it as polarization of a bond. And this polarization will always be permanent because atom B will always be more electronegative than atom A. So a permanent polarization of a sigma covalent bond has taken place due to differing electronegativities of 2 atoms. And my dear student, this permanent polarization of a sigma covalent bond due to difference in the electronegativities of 2 atoms is what we simply call it as the inductive effect. So everyone, inductive effect is permanent polarization of a sigma covalent bond towards more electronegative atom due to differences in the electronegativities of 2 atoms. Now, when you talk about polarization, if we try to understand the same phenomena in terms of the electron density, how exactly does this looks like? Well, so to understand this, let's take this case. Let us say we have got atom A and atom B, which are having not much of a differences in their electronegativities. So what happens? Let's say the electron density between atom A and B I'm representing with this dots. So dots indicating electron cloud. Hold on everyone. Well, what I'm drawing right now is the electron density which is shared between the atom A and atom B, but because these 2 atoms are not differing in their electronegativities to much of an extent, I will say the electron density is symmetrically shared between atom A and B. But now if you consider second scenario, which is the case of inductive effect, assuming atom B is more electronegative than atom A, so what will happen? The same electron density which you now see symmetrically shared will be now pulled by atom B because of its more electronegativity. So after this electron density gets shifted towards atom B, it will appear like this. This is just an electron cloud representation, okay? Just to make you understand that now electron density is no more symmetrically distributed. It is now shifted more in favor of atom B because of its higher electronegativity than atom A. So guys, if we consider these 2 scenarios, we realize that in case of first representation, atom A and atom B are sharing electron clouds symmetrically, hence there is no bond polarization. Whereas In the second case, atom B being more electronegative, the electron density have been shifted more in favor of B. So I will say this represents the polarization of a sigma covalent bond. Just to put this in terms of example, let me show you. Let's say if we have got methyl chloride, okay everyone? So that's how we can represent methyl chloride. Now in case of this methyl chloride, we know that atom chlorine is more electronegative than atom carbon. Because chlorine is more electronegative, it will pull the bonding pair of electron towards itself, and hence chlorine will acquire delta minus and the carbon will acquire delta plus charge. This is going to be a permanent polarization of a sigma covalent bond, and you'll call this is the inductive effect which is operated between the two atoms. So everyone, whatever we have learned, if we try to put it together in the form of characteristics of inductive effect, we would say inductive effect is a permanent polarization of a bond. It takes place between the two atoms differing in their electronegativities. For such kind of inductive effect to take place, we don't need any external reaction, because it will always take place if there is differences in the electronegativities. Now guys, let's have a look at the types of inductive effect. Again, just now we took example of methyl chloride. I'm just representing halogen as X. Now, halogen atom being more electronegative will pull the bonding pair of electron towards itself. Now, I want you all to focus on this group. Look at this. In terms of methyl group which is connected to halogen, in terms of methyl I'm saying, can I say it appears like this methyl group is donating electron to the halogen atom. This methyl group is donating electron to halogen atom. Such an atom or a group of atom who donates electron or releases electrons to another atom, we call it as electron donating groups. So methyl is EDG, electron donating group. Sometimes you will see people will refer it as ERG, that is electron releasing group, one and the same thing. So when any atom or a group of atom that donates electron to another atom, we call it as EDG. And the effect of donation of electron to other atom through a sigma covalent bond is what you call it as plus I effect. So the electron releasing inductive effect is what you call it as plus I effect. So all those groups which are electron donating group will always show an effect of plus I effect. So here we have listed several groups which are capable of showing electron donating inductive effect, but let's just have a look at their decreasing order of ability of releasing electrons. So guys, when you talk about O minus is the one which shows the highest electron releasing inductive effect, followed by the carboxylate ions, followed by, if you see, we have got all the alkyl groups in which more substituted alkyl, that is tertiary alkyl, will show the highest plus I effect among the alkyl I'm saying, followed by a carbon connected to two other carbons, so that is secondary alkyl group, followed by we have got primary alkyl group, and relatively lesser electron donating effect is shown by methyl, and then you can see tritium, deuterium, and then hydrogen atom. Generally hydrogen we consider it as a reference atom. So guys, these are several electron donating groups, and this is the decreasing order of their tendencies of releasing electron to another atom via sigma covalent bond. Similarly, there's another inductive effect which we call it as minus I effect. We have taken again the same example. Everyone here? You will see halogen connected to the alkyl group, precisely speaking methyl. So halogen being more electronegative, withdrawing electron towards itself, as a result of which acquiring delta minus and leaving delta plus charge on the carbon atom. Now dear student, I want you all to focus on the halogen atom and not on the methyl group. So when you look at this halogen, it appears like this halogen atom is now withdrawing electron towards itself from the carbon atom of methyl. Such an atom or a group of atom which withdraws electron towards itself, we call it as electron withdrawing group or electron pulling group. and the effect of withdrawal electron from another atom through sigma covalent bond is what we call it as minus I effect. So guys, just like we had plus I effect, we have got minus I effect. So all those atom or a group of atom who will withdraw electrons from another atom are going to show minus I effect. So let me show you all the various groups which can show this kind of minus I effect in their decreasing order is, you will see Nr3 plus, NH3 plus. Well, when we study Friedel-Crafts alkylations limitation, that time we know how NH2 group turns into NH3 plus and shows minus I effect. Also, when you talk about the reactions of aromatic amines, we know that aniline contains benzene ring carrying NH2, which should be ortho-para directing. But due to protonation of that NH2, it becomes NH3 plus. It becomes deactivating and meta directing. So one of the reason you can see here, because NH3 plus is withdrawing group. So other than that, we have got nitro, the more commonly used electron withdrawing group, nitro, followed by cyanide, fluoride, carboxylic acid, carbonyl carbon, chlorine, bromine. So all the halogens here, followed by iodine, OH, alkoxy, and then alkyne, alkene, and then the reference atom is hydrogen atom. So guys, what we have studied is all about inductive effect and its type. Let me just summarize what we have seen. So inductive effect is a permanent polarization of a sigma covalent bond that occurs due to differences in the electronegativities of two atoms. And we don't really need any external reagent for this effect to carry out or to take place. These effects are of two types, plus I and minus I. The electron donation effect shown by electron donating group is what you call it as plus I. And the electron withdrawing effect through the sigma bond by electron withdrawing group is what you call it as minus I effect. Guys, that was all about the inductive effect. Are we all here, everyone? Let me see you guys in the chat box. Are you all understanding, everyone? All right. Excellent. So good to see you guys responding so quickly. Lovely, everyone. Chalo, let's get started further. So that's what all about the inductive effect. Next one, let's talk about electromeric effect. Well, when you talk about application of electronic effects, electromeric effect is not that often asked, but we'll just see as a reference or as one of the concepts. Well, guys, let's assume we have got an alkene and we are allowing that alkene to react with some electrophile. Let me remind you, we have studied that nucleophiles we categorize into four classes: anionic, neutral, pi bonded, and ambident nucleophile, out of which the third category we are talking here. We are talking about alkenes. Because alkene contains pi bond, they belongs to a category of a pi bonded nucleophile. Because they are pi bonded nucleophile, they'll always have a tendency to attack at electron deficient species such as electrophile. Hence, we have taken this example where let's assume that alkene is brought in contact with some electrophile. So because alkenes are pi bonded nucleophile, they'll have a tendency to attack at electrophile. But for that attack to take place, this pi bond will break towards one of the atom. So see what is happening now. In the previous case, sigma bond or sigma electron density was shifting towards more electronegative atom. But here there is not just a shift. Here it is the complete transfer of pi electron towards one of the atom. So this complete transfer of pi electron towards one of the atom will make an atom electron rich where the pi electrons has transmitted, and the other atom will become electron deficient. The moment this become electron rich atom, now this atom is eligible to attack at the electron deficient species, right? So guys, isn't it a movement of electron? Yes, it is. But the electrons which are now moving are not sigma electrons, they are pi electrons. Another difference, it is not just a shift, it's a complete transfer of pi electron. Now, once the pi electron have been transmitted towards one of the atom, it is now ready to attack at electrophile. But imagine, hypothetically, if I remove this electrophile from here, then this negative charge will delocalize back towards the deficient carbon and you will get back your original alkene. Which means this complete transfer of pi electron towards one of the atom is not permanent, it's a temporary effect. Hence we say temporary but complete transfer of pi electrons towards one of the atom in presence of attacking reagent is what you call it as electromeric effect. So guys, inductive effect is a property of a sigma bond. Electromeric effect is a property of a pi bond. So some of the simple characteristics on your screen, it's a temporary effect, whereas inductive effect was permanent. It involves complete transfer of pi electron. In case of inductive effect, it was just a shift of sigma electron density. And for this effect to take place, it is necessary that we have attacking reagent. Whereas in inductive effect, the presence of attacking reagent is not necessary. So guys, that was all about electromeric effect. And now we are going to proceed with the most important electronic effect from the journal Organic Chemistry, that is resonance. Guys, I want you all to pay attention to this first. Everyone, are you there? Everybody, are you there? All right. Great, guys. Chalo. So before we learn a concept of resonance, you need to understand a term called as delocalization or conjugation. Well, in simple words, if we have to put delocalization or conjugation, I would say it is nothing but the flow of electron density from one part of a molecule to another part of molecule. Conjugation or delocalization is nothing but flow of electron density from one part of a molecule to another part of molecule. So naturally, if we have got a molecule having two sites, one of which is highly electron dense and other is electron deficient, then naturally electron density will always flow from highly dense area to a lower density area, isn't it? So what are those different types of cases where you will see electron density can flow or can move? So there are several cases which you will see in organic compounds where electron density will be able to flow from highly dense area to lower density area. Whenever such electron density moves or flows from one part of molecule to another part of molecule, in simple words, we say the conjugation has taken place or delocalization has taken place. Look at the term delocalization. When you say there is something static, you say something is localized. So if electron density is present on any of the atom, you will say the density is localized. But the moment it starts flowing or if it moves, you will say the delocalization is taking place. So guys, several cases under which the conjugation or delocalization can take place are right in front of you. The first one is where pi bond is in conjugation with the vacant orbital. Just to read it in easiest way, you can say pi bond alternate to vacant orbital. For example, look here. Look. Everyone, the example we have got is allyl carbocation. You see CH2 double bond CH, single bond CH2 plus. If you look at this carbon atom, the positively charged carbon is in sp2 hybridized state. So it has one vacant p orbital. So atom having vacant orbital is alternate to another atom carrying pi bond. Hence we are referring it as pi bond alternate to the vacant orbital. So this indicates that pi bond, we know the fact that the pi bond is a weaker bond as compared to sigma bond. If it is a weaker bond, which means electron density in the form of pi bond is loosely held. So such electron density will always have a tendency to flow down to the deficient area. Hence, I'll say in a molecule, this is electron dense area, this is a deficient area. So pi electron will delocalize towards the deficient atom. Now, due to this delocalization or conjugation, a structure will be now converted to another structure, which I'm writing like this. You can see atoms hasn't changed. The sigma bond hasn't changed. So CH2, CH. Now this cationic carbon became doubly bonded, but this carbon lost its electron, so it will become deficient. So everyone, what has happened? In case of molecule where there was pi bond in conjugation with vacant orbital, electron density has moved from pi bond to vacant orbital, and as a result of which we got another structure. Fine. So the structure obtained as a result of conjugation. Similarly, we may have another case where the conjugation can take place other than pi bond in conjugation with vacant orbital. The second one is pi bond in conjugation with the negative charge. Have a look at this, everyone. Just like we had allyl carbocation, if I make this cationic carbon anionic, I'll call this as allyl carb anion. Right, everyone? Well, so in this allyl carbon ion, I have got two atoms sharing pi bond and another atom carrying a kind of lone pair or anionic carbon atom. See, when you talk about lone pair or electron pair held by one of the atom, and there is pi electron pair which is held between the two atoms. So if you compare electron density shared between the two atoms and electron density held by just one atom, can we logically say that when atom is holding the entire electron pair is more electron rich because of higher density than the another atoms which are sharing the pi electron cloud? This indicates the negative charged carbon atom is the highly dense area as compared to pi bond. Hence the density will flow from negative charge to pi bond. Let's say this negative charge is delocalizing towards the atom, making carbon pentavalent, so this pi bond will shift further to the doubly bonded carbon atom. And if that happens, we will be getting another structure as a result of delocalization, which is CH2 electron pair minus single bond CH double bond CH2, guys. So this is yet another condition which is responsible for the conjugation to take place. Likewise, we'll be seeing some more conditions here. The third one for you all is pi bond in conjugation with a lone pair. Pi bond in conjugation with lone pair, once again, atom carrying lone pair is more dense than the atom which are sharing pi bond. Hence, the flow of electron will be from lone pair carrying atom to pi bond. You can also say this as lone to pi bond. So lone to pi bond delocalization would be like this. If this lone pair delocalizes here, this carbon will become pentavalent, which in turn will push the pi bond onto the terminal carbon atom. Dear student, if that happens, what are we going to get? We will be getting CH2. CH2, hold on everyone. CH2 single bond CH double bond NH2. Well, here you will see the terminal carbon atom got an electron pair, so it became rich. Nitrogen shared its lone pair, so it will be deficient in one electron, and that's how the charge on the nitrogen will be developed. So we got another structure as a result of conjugation where the lone pair was in conjugation with the pi bond. So guys, so far we have studied three conditions where conjugation can take place. First one was pi bond in conjugation with vacant orbital. In some books you might see it is referred as positive charge, but the precise, or you can say the more appropriate term would be to refer it as a vacant orbital. Second one was pi bond in conjugation with the negative charge, and the third one we have got right here, pi bond in conjugation with the lone pair. And the fourth one we have got pi bond in conjugation with the pi bond. I want you all to look at this structure. I'm referring it as structure number 1. Well, everyone here, pi bond in conjugation with pi bond. Now, since both the atoms holding these pi bonds being identical, the flow of electron density can be from any of the pi bond to any other pi bonds. So let's say I'm delocalizing this pi bond from left to right. So this pi bond will delocalize here, making carbon pentavalent. So this pi bond will shift further onto terminal carbon. If that happens, you will see the pi bond will shift between 2 and 3, which you can see here. And the terminal carbon has received another pi bond, so that will become electron rich, so charge will be minus. Similarly, this carbon atom has lost its electron, so it is becoming deficient. So we got one of the structure, I'm calling it as structure number 2, as a result of conjugation or delocalization. Well, the flow of electron which I have represented here was from left to right. The same can happen from right to left. So if that happens, let's say pi bond delocalizing here, another pi bond shifting on to the terminal carbon. Let's call it 1, carbon number 1. So double bond will be between 2 and 3. Carbon number 1 is now becoming electron rich, and the fourth one is becoming electron deficient. Dear student, I am calling this structure as structure number 3. Now again, some of you might be in the question mark with, so what's the difference between 2 and 3? These two are identical. They are same. Are they? Well, let me tell you, structure number 2 and 3, they are similar, but they are not same. Simply to understand, imagine if I isotopically label one of the carbon. Let's say this carbon number 1, I'm making it as C14 carbon. So as a result of delocalization from left to right, the C14 carbon would become deficient. But in another structure, due to conjugation, meaning if you move electron from left to right, the C14 carbon is going to become electron rich. That indicates this two structure, number 2 and number 3, are similar structure, but they are not same, which means you have to treat these two as a different structures obtained as a result of conjugation. Everyone, are you getting that? Everyone? All right. Okay, guys. Chalo. So that was the fourth condition. Similarly, if you talk about the fifth one, where pi bond is in conjugation with odd electron, look here. So odd electron carrying atom indicate it has got only 7 electrons in its valence shell. 3 sigma bonds and 1 odd electron, that is 7 electron. 7 electron also indicate it is electron deficient center. Whereas this odd electron carrying atom is in conjugation with the pi bond. So pi bond carrying atom is electron rich part of molecule, and the odd electron carrying species is a deficient part of molecule. So naturally, the flow of electron will be from pi bond to an odd electron carrying atom. But my question is, can we directly delocalize the entire pi bond towards the deficient carbon atom? Well, think logically. If you do it, what will happen? If I delocalize this pi bond towards the odd electron carrying atom, this odd electron carrying atom already having 7 electrons in the valence shell, if entire pi bond is delocalized over there, that carbon will receive 9 electrons. So it will have more than 8 electrons, which means we are not supposed to delocalize the entire pi bond. In fact, naturally by itself, it won't happen like that. So what happens is, the pi bond will first undergo homolytic fission. Homolytic fission we represent by the fish hooked arrow. So this carbon will be carrying odd electron, and this odd electron will be shared to form a pi bond here. And one of the electron have been now settling at this first carbon atom. So as a result of conjugation, what we are getting here is CH2 odd electron, single bond, CH double bond, CH2. So guys, we got another structure as a result of delocalization. Now, the sixth condition, if you see anywhere atom carrying lone pair is in conjugation with the pi bond, this clearly indicates that the lone pair carrying atom is the electron rich area and the deficient atom is deficient, of course. So the lone pair will delocalize into the vacant orbital. This is also the condition which we refer it as a back bonding, right? So lone pair delocalized back, as a result of which we got CH2. Now here we got double bond, oxygen carrying one lone pair and one methyl at the other end. But because oxygen has shared one of its electron pair, it will acquire a positive charge on it. So we got another structure. So guys, now what happened in all these cases? Well, we started our discussion in order to learn phenomena of a resonance. But I said before you learn resonance, you need to understand the term called as conjugation and delocalization. So we referred conjugation or delocalization as flow of electron density from highly dense area to a low density area. Now several cases where such things will arise, that is high density area to low density area, are the first one which we saw was pi bond in conjugation with vacant orbital. Second one was pi bond in conjugation with negative charge. Third one was pi bond in conjugation with lone pair. Fourth one, pi bond in conjugation with pi bond. The fifth one was pi bond in conjugation with odd electron. And finally, lone pair in conjugation with vacant orbital. Now guys, in all these cases, we had a high density area to low density area. So what happened? Look, let's say if I'm saying I had a positive charge here. Whenever you have a positive charge or any negative charge, if that charge increases, we say accumulation of charge taking place. If there is accumulation of a charge, the energy of that molecule increases and molecule becomes less stable. If positive or negative charge increases, we say accumulation of charge takes place and the energy of molecule increases and it becomes less stable. On the other hand, if any part of molecule is carrying any charge, if that charge is dispersed, if that charge is spread over adjacent atoms, then that dispersal of charge will always lower down the energy of molecule, and hence in turn it will make the molecule more stable. So guys, if you look at all this condition that we have talked about, let us begin with the first one. Pi bond in conjugation with vacant orbital. We had a positive charge here, but due to this delocalization or due to this conjugation, you can see positive charge spread over from carbon number 1 to carbon number 3 in another structure. So this is nothing but dispersal of charge. You can see that here as well. Let's assume this is carbon number 1, 2 and 3. So carbon number 3 had a negative charge, but as a result of the delocalization or conjugation, negative charge have been dispersed from the third carbon atom to carbon number 1. And like I said, dispersal of charge or spreading the charge over molecule or a part of molecule will lower down the energy and hence will stabilize the molecule. That's why guys, all this condition of conjugation and delocalization are in turn lowering the energy of molecule and hence stabilizing them. So guys, these are the conditions which are responsible for the phenomena of a resonance takes place, because resonance involves the delocalization of a lone pair and a pi bond. So if any of this condition arises, we say phenomena of a resonance is taking place. Now to understand what is resonance, let me just take simple example. Everyone, we have been learning that compound is acidic when the conjugate base is stable, isn't it? We have been learning that compound is acidic when the conjugate base is stable. So let's say today we have to prove that RCOH, carboxylic acid, is acidic in nature. How would we do that? A very simple way. In order to justify that the compound is acidic, I will prove that its conjugate base is stable. Hence what I did is I converted carboxylic acid into its conjugate base. You can see here, acid lost H plus ion, let's say. Acid donated H plus ion. So I'm breaking the bond of O and H in favor of oxygen. So the bond pair will be taken by O, making it electron rich, and the H is lost as H plus. Well, for this reaction to proceed in the forward direction, what should happen? I would say this compound can donate H plus ion when the corresponding anion form is stable. Think logically. If this anion form is stable, then equilibrium would not mind shifting in the forward direction, because even after the breaking of a bond, the anion form is stable. So if anion form is stable, then this molecule will always lose H plus ion, of course in water. So such compound would donate H plus ion, we call it as an acid. But this anion which is formed, we also call it as a conjugate base of carboxylic acid. So if this compound has to behave as an acid, its conjugate base which is formed has to be stabilized. So let us justify that this is stable. So I took this carboxylate ion over here. You see one and the same thing here. Let's number this as oxygen 1 and this is oxygen number 2. Guys, firstly I want you all to focus on this structure and tell me, out of as many conditions we studied for conjugation and delocalization, which one do you observe here? Which one do you observe? Yes, can I see that in chat, everyone? Okay. All right, guys. Yes, of course, you can see here negative charge is in conjugation with pi bond. Yes, negative charge is in conjugation with the pi bond. So negative charge is more dense area than the pi bond. So naturally, flow of electron density will be from negative charge to pi bond. So if this negative charge delocalizes, carbon will become pentavalent. So pi bond will go back on carbon number 1. If that happens, we will get another structure separated by a double headed arrow, where between oxygen number 2 and carbon there will be double bond. So this is O2. And between O1 and C there will be single bond, so that is O1. But oxygen number 1 is becoming electron rich. Again, in this molecule as well, we have got negative charge is in conjugation with the pi bond. If you delocalize it back, the pi bond will go back on O2, and you'll get once again the starting structure from where you began this conjugation. So guys, as a result of delocalization of lone pair and a pi bond, I got two structures here. Okay. Now let us consider one of the structure out of these two. I am considering structure number 1, and I'm trying to find out 3 bond parameters of this structure, which are bond order, bond energy, and bond length. Pay attention, everyone. So if you look at structure number 1, and if you find out the bond order of O1C and O2C, bond order is nothing but number of covalent bonds shared between the two atoms in a simple words. So between O1 and C, how many bonds do you see? 2. So bond order for O1C is 2. And that of O2 and C, the bond order in structure number 1, because we are talking for structure number 1, it is just 1. Let's put it here. Okay. Second bond parameter we are learning is bond energy. Well, if bond order is 2, bond order 2 meaning the bond length will be shorter and the bond strength will be higher. So energy required to break O1C bond will be more than O2C bond. So let's say for O1C, energy required is E1, and for O2C, energy required is E2. So if you compare E1 and E2, you will say E1 is more than that of E2. Isn't it, everyone? Yes, we will say that. Bond length, well, more the bond order, shorter the bond length, meaning O1C will be shorter bond than O2C. So if I say O1C bond length is L1 and O2C bond length is L2, then I will say L1 is shorter than L2. So guys, these are some of the bond parameters which we have jotted down by looking at the structure on screen, right? Now think, what if I asked you to find out the same bond parameter for structure number 2? So for structure number 2, O1C bond order will become 1, O2C bond order will become 2. So the value will be reversed. If O1C bond order is 1, then this is gonna be a weaker bond. So E1 will be lesser than that of E2. Similarly, because this is single bond, this will be longer. So L1 will be greater than L2. So all the values which we have got here for structure number 1 will be reversed if we compare those values for structure number 2. Isn't it, everyone? Now what we did is, by looking at these two structures, we tried to find out the actual bond parameters for this O1C and O2C experimentally. When we actually found out these values experimentally, we realized that the bond order was neither 1 nor 2. It was found to be 1.5. Whereas bond energy E1 and E2 wasn't lesser or higher. In fact, E1 was found to be equal to E2. Similarly, the bond length for O1C as well as O2C was found to be equal. Guys, what does this indicate? Tell me, these are the real values of bond parameters which we obtain experimentally. Tell me, are these values matching with the values which we have got by looking at the structure? No, it is not. What does that mean? That means this structure which are not corresponding to this value. See, these values are not corresponding to the structures. But we know the fact that these all are the real values. If these are the real values, and if the structures are not corresponding to those real values, which means this is not the real structure. So what is the real structure? Hence, to draw the real structure, then we draw an average of this. So let's say I'm drawing an average structure of this too. How to get an average structure? Well, firstly, I'll put down all those which hasn't changed. What hasn't changed? Position of atom hasn't changed. Sigma bonds hasn't changed. They never moved. So I'll write down that first. So I'll have R, single bond, C, Single bond O, and every O is anyways carrying 2 lone pair. Another O carrying 2 lone pair. Right, everyone? Now see, since I have to draw an average, what I'll do now, if I compare structure number 1, double bond is between O and C. Structure number 2 says no, double bond is between O2 and C. Meaning that pi bond is neither permanent between O and C nor between O2C. It is shared between O1C to O2C. So I'm showing a partial pi bond because it is being delocalizing between O1C and O2C. Also, if you talk about the charges, structure number 1 says -1 charge is on O2 and structure number 2 says -1 charge is on O1, meaning -1 charge is neither permanent on O1 nor on O2. It is shared by O1 as well as O2. So the charge carried by each atom will be -1 shared between the two. So every oxygen will have a charge of -1/2. Now guys, I am saying this is the average structure of this two. Let's try and relate the real values with this structure. What were the real values? Bond order was 1.5. Is it? Yes, it is. Then the bond energy E1 and E2 are equal. Of course they are, because I can see both the bond orders are identical and also bond length are also equal, which means everyone, all these real values which we got here experimentally are perfectly matching with this structure. That indicate this is our real structure and not the previous one. This real structure which we have got, dear student, this structure is what you call it as resonance hybrid. This is what we refer it as resonance hybrid. And all the other structures from which we got the resonance hybrid are known as resonating structures. So keeping all this point in mind, if I just try to define resonance, I would say, see what we did. For given carboxylate ion, I had to prove that this is a conjugate base which is stable. Now, am I in position to say that this is stable? Yes, I am. Because in this molecule, negative charge got dispersed, you see, from O2 to O1. Whenever there is dispersal of charge, we say there is lowering in the energy. Lower the energy of molecule, more is the stability of molecule, which means this structure number 1, or you can say the carboxylate ion, is stabilized as a result of dispersal of a negative charge. But the dispersal of a negative charge gave me two structure along with an average structure which is called resonance hybrid. But when I compared the real values, none of the structure 1 or 2 alone was able to justify the properties which I got experimentally. Hence I will say, whenever we draw 2 or more number of contributing structures of a given compound such that none of the structure alone can explain all the properties, like we saw experimentally obtain 1. So when none of the structure alone can explain all the properties, we draw an average structure. That average structure is what you call it as resonance hybrid, and all the contributing structure from which this hybrid is obtained, dear student, we call them as resonating structure or canonical form. And the phenomena by which these structures are obtained is what you call it as resonance. So tell me, dears, if I look at this molecule, these two structures we have obtained as a result of what? As a result of delocalization of lone pair and a pi bond. Hence, this phenomena of a delocalization or conjugation of a lone pair and a pi bond is what you call it as resonance. And as a result of this resonance, we can see the negative charge got dispersed. That indicates resonance phenomena is the one which helps us to stabilize the molecule. So guys, when you talk about inductive effect, electromeric effect and resonance effect, you will see the difference in all these three electronic effects. Inductive effect was taking place as a result of shift of sigma electron density. Electromeric effect was taking place as a result of complete transfer of pi electrons. And the resonance effect takes place as a result of the delocalization of a lone pair and a pi bond. Sometimes it could be just a presence of pi bond as well. And In any of these cases, if there is a dispersal of charge taking place, then I'll say all these effects are helping or contributing towards lowering the energy of molecule, meaning stabilizing the molecule. So guys, just like we had inductive effect were of two types, even resonance effect is of two types. So let me just first brief you what we studied. What was resonance, everyone? When two or more contributing structures of a compound can be drawn such that none of the structure alone can explain all its property. So what do? We draw an average structure. That average structure is known as resonance hybrid, and all the contributing structure we call it as resonating structure, and the phenomena by which those structure are obtained, meaning delocalization or conjugation, is what you call it as phenomena of resonance. This resonance could be of two type. Again, you can call it resonance effect or mesomeric effect. Like I said, as of now, we are not getting into that difference of resonance and mesomeric effect. Let's treat them one and the same thing for the time being. So everyone, if you ignore this OH, can I say the remaining part is a conjugated system? Yes, we can see pi bond, alternate pi bond, meaning pi bond is in conjugation with the pi bond. Now let's assume we introduced a group called OH in already existing conjugated system. Now the moment I introduce OH group in this conjugated system, the first atom of OH group is carrying lone pair. So these lone pair are now again coming in the conjugation with the pi bond. So you can see conjugation has extended. Pi alternate pi was already there. Now again in conjugation I have got lone pair. But if I compare lone pair and a pi bond, tell me everyone, from where to where electron density will flow? Yes, everyone, I'm expecting you all to write it in the chat. Come on. From where do we expect electron density to flow? We expect it to flow from highly dense area to low density. So lone pair are more loosely held. Hence, it is relatively higher density area. So lone pair got delocalized. So this carbon became pi bond. So this pi bond delocalized further, making this carbon pentavalent. So eventually this pi bond settle on the terminal carbon. What I want you all to look at is the OH group. Guys, looking at this, tell me what's happening. An atom or a group of atom is releasing electron to the conjugated system. Such an atom or a group of atom who donates electron, we call it as electron donating group. And the effect of donation of electron to the conjugated system via lone pair and a pi bond is what you call it as plus M effect. That is, in simple word, you can say positive mesomeric effect, just like we had plus psi effect. Guys, wherever you see there is donation taking place, wherever you see there is donation of electron taking place, we will always refer it as plus effect. And whenever you see there is withdrawal, we'll always refer it as minus effect. So guys, because in this molecule, the group has released its electron to the conjugated system, I'll call it as plus M effect. So which all group capable of showing this kind of plus M effect? Logically, if any group has first atom carrying lone pair, will be eligible to release electron. Hence, all those group will show plus M effect. So you can see several examples here. We have OH, ORL coxy, NH2, NHRC. The first atom everywhere is carrying lone pair. Thioalcohol, then SR, halogen. All these group where the first atom carries lone pair will always release electron to the conjugated system, and you will say that group is showing plus M effect. Just like plus M, think of minus M as well. So we have got existing conjugated system to which I attached a group called NO2. Now, if you look at this NO2, the first atom of the group isn't carrying lone pair like in previous case. In fact, the first atom of the group is multiple bonded, connected to more electronegative atom than itself. I repeat, the first atom is doubly bonded. Double or triple, we refer it as multiple bond. So I'm saying the first atom of the group is multiple bonded attached to more electronegative atom than itself. So naturally, if O is more electronegative, the pi bond will break towards oxygen, making this nitrogen more electron deficient. So such deficient atom, rather than donating electron, will withdraw electron towards itself, isn't it? if such withdrawal takes place. So this clearly indicates that this nitro group is now withdrawing electron towards itself. So I'm referring it as electron withdrawing group. And the effect of withdrawal of electron to lone pair and a pi bond is what you call it as minus M effect. Whenever you see there is donation of lone pair or a pi bond, call it plus M. Whenever you see there is withdrawal of electron through the pi bond, you call it as minus M effect. So guys, can we simplify and say all those group whose first atom will be multiple bond connected to more electronegative atom will always show minus M effect. For example, aldehyde. Look at the first atom carbon, doubly bonded connected to oxygen which is more electronegative. We have got again, just like aldehyde, we have got ketone or even nitrile, C triple bond N. So the first atom is carbon, lesser electronegative, but multiple bonded connected to more electronegative atom. So even this is withdrawing. Carboxylic acid is withdrawing. Sulfonic acid is also a withdrawing group via minus M effect. So guys, these are the two types of resonance effect. So just like we had plus I minus I, you will see often we use term called as plus M minus M, or sometime they also call it as plus R and minus R, but the preferred one is plus M and minus M. Now that we have learned the phenomena of resonance, guys, taking you straight away to its application, that is to understand the phenomena of aromaticity. Well, you can say this is kind of the application of resonance effect. And everyone, once this concept is done, straight away I'm going to take you to the previous year question just to make you understand how are this concept being utilized in framing the question in the competitive examination. Before which, let us learn aromaticity. Well, just to brief you, keeping the timeline of this marathon lecture in mind, of course I'm going to go a little faster. So when you say a compound is aromatic, well, for any compound to be called as aromatic, there are four criteria which has to be satisfied by that compound, which is a molecule needs to be cyclic, it needs to be planar. Well, now when do we say a molecule is planar? Well, all the atoms are in sp2 hybridized state. If the atoms of molecule forming that cyclic structure are in sp2 hybridized state, then we will say that molecule is planar. Now, when you talk about organic compound, naturally we refer more to carbon containing compound. So when you have got a carbon in a doubly bonded state, so when you say the carbon will be sp2 hybridized, whenever you see a carbon which is doubly bonded. Okay, so again we have got 3 sigma bond and assume this is one of the pi bonds. So if you see doubly bonded carbon or cationic carbon, again since I have got 3 sigma bonds, steric number is 3 meaning sp2. So a carbon which is doubly bonded or cationic carbon, or at times you might see organic compound containing another atom like boron. So even if you see boron which is with 3 sigma bond, even this atom will be in sp2 hybridized state. So wherever you see organic compound where carbon is either doubly bonded, cationic or a boron, then in such case you will say that all the atoms are in sp2, and then you will say that the molecule is planar. But if you have any atom which is other than carbon and boron, like heteroatom, meaning lone pair containing oxygen or lone pair containing nitrogen, then how do we find out whether it is sp2 or not? We are going to see that. But for the timing, out of 4 criteria, first is a molecule should be cyclic, it should be planar, and it should have a complete conjugation of a pi bond and a lone pair if there is a lone pair. What does complete conjugation mean? Well, let's say everyone, I have got a molecule like this. This is cyclohexane, this is cyclohexadiene. Okay. Well, everyone, if you see this molecule, there is a conjugation. I'm not denying that fact. Pi bond in conjugation with pi bond, or in simple words, pi bond alternate pi bond. There is a conjugation. But conjugation is starting from, let's say, carbon number 1 and it is ending at carbon number 4. I don't have a further conjugation. So when I'm referring a term completely conjugated, meaning the conjugation should be in a completely in the molecule, inducing a complete ring current, meaning from wherever you are starting the conjugation, you should end up with that atom as a conjugation, like pi alternate pi. Suppose if I put one more pi bond here, like a benzene, I will say now this molecule has a complete conjugation. How come? Pi bond, alternate pi bond, alternate pi bond, alternate pi bond. So from where I began, I have reached to the same atom considering the conjugation of a pi bond. So now I'll say this molecule is completely conjugated. And other than that, the total number of pi electron present in the molecule should be according to the Halide rule of aromaticity, which means a molecule should have 4n plus 2 pi electrons, where the value of n could be 0, 1, 2, 3, so on and so forth. Meaning in simple words, imagine if I put the value of n as 0. So 4 into 0, 0, meaning you should have either 2 pi electron in a cyclic molecule. If you put the value of n as 1, 4 ones are 4 plus 2, that is 6 pi electron, like in benzene. 3 pi bond meaning 6 pi electron. Or if you put the value of n as 2, 4 2s are 8 plus 2, that is 10 pi electrons, so on and so forth. If your molecule satisfy these 4 criteria, you will say the molecule is aromatic in nature. So just to take an example, I'm going to take example of benzene. But before that, let me tell you, you might find some atom carrying lone pair, which would be deceptive. Sometime you might feel that atom is in sp2 hybridized state. Sometime it might look like it is in sp3, but it won't be in sp3 hybridized state. For example, everyone, there's a concept called as localized and delocalizable lone pair. In short, I'm explaining it to you guys here. Okay. To understand that, let's say I've got molecule like pyrrole, where n carrying a lone pair. In simple terms, if I ask you, what do you think is hybridized state of nitrogen atom? With all your basic calculation, what will you do? You'll count the number of sigma bond plus lone pair. So this nitrogen has 3 sigma bond, 1, 2 and 3, plus 1 lone pair, 3 plus 1, 4. If steric number is 4, of course, you'll end up saying that this atom is in sp3 hybridized state. But that isn't the case. This lone pair, everyone, let us try and find out whether this lone pair are delocalizable or are they localized. How do you find it out? Well, if you see in any molecule the lone pair, theoretically, if you see that they are in conjugation with any pi bond, then actually whether they are going to delocalize in the conjugation or not can be checked by assuming that they are getting delocalized and writing the corresponding resonating structure and checking the feasibility of that structure. What I mean to say is, as of now, I see this lone pair are in conjugation with the pi bond. So if I see that they are in conjugation with pi bond, let them delocalize. Suppose I delocalize it here, this pi bond will go back on the carbon. If that happens, then this structure will exist in another resonance form like this. Everyone here? Now there will be new pi bond here, so nitrogen will acquire positive charge and this carbon will become electronless. So the structure which I have obtained is as a result of delocalization of a lone pair. So the lone pair which were theoretically looking like they are delocalizable, whether or not they will actually delocalize, to know that I delocalized them and I got the structure. Now check the feasibility of this structure. Feasibility meaning what? After delocalization, look at this nitrogen. What is the hybridized state of nitrogen in here? Now this nitrogen has only 3 sigma bond, 1, 2 and 3. Pi bond we never count for hybridization state, right? So I have got only 3 sigma bond, 3 sigma bond meaning sp2. And we said in a cyclic molecule, sp2 hybridized state of atom is feasible. It is possible because sp2 hybridized state will demand geometry to be trigonal planar, and that geometry can be acquired by an atom in a cyclic molecule. So because after delocalization of a lone pair, that atom became sp2 hybridized, which is a feasible geometry of that atom, I will say that this lone pair will delocalize, because even after delocalization, the atom is existing in its possible hybridized state. So such lone pair will never be counted as a lone pair. Such lone pair, you'll count them as a pi bond. Hence, If anyone asks you how many are pi electron in this molecule, you will say this 2 pi bond you already see, meaning 4 electron. Because these lone pair are delocalizable, after delocalization even that is going to be a pi bond. So I'll consider this lone pair also as pi electrons. So total number of pi electrons are 6. 2 in the form of pi bond directly, 1 which is delocalizable. So such lone pair I'll call them as delocalizable lone pair. Whereas if you consider a case of pyridine, let's say we have got pyridine now. Look, in this pyridine, again we see a nitrogen atom carrying lone pair, which theoretically seems like it is in conjugation with the pi bond, isn't it? Yes, it does look like lone alternate pi bond. But whether or not it is actually delocalizable, to check that, what do? We actually delocalize and check the feasibility, possibility of existence of a structure form. So let's say I delocalize it. Lone pair delocalized towards pi bond. Pi bond went up on carbon. That resulted in structure like this. So pi, this became anionic carbon. And now see this lone pair delocalized here. So nitrogen acquired positive charge. Now guys, let's talk about the feasibility of this structure. Is this structure going to exist as a stable one or not? Well, what do you see here? We see the nitrogen atom has only 2 sigma bond, 1 and 2, isn't it? If this nitrogen has only 2 sigma bonds, meaning what is the hybridized state? sp. Now when any atom exists in sp hybridized state, what geometry will it demand? sp hybridized atom demand geometry to be linear. Linear meaning all the bonds has to be in a line. So tell me, in a cyclic structure, can any atom acquire linear geometry? It cannot. Because this nitrogen won't be able to acquire a linear geometry, I'll say this nitrogen cannot exist in sp hybridized state, meaning this state of nitrogen atom is not possible, meaning this pi bond cannot be formed, meaning this lone pair cannot delocalize. Why? Because after delocalization it is turning this nitrogen atom into sp hybridized state, which will demand geometry to be linear, which is not going to be possible. So this is not a feasible structure. So these lone pair are called as non-delocalizable lone pair, or you can also call them as localized lone pair. So they are delocalizable, they are called localized lone pair. So such localized lone pair will always be considered as a lone pair. We'll never count them for a pi bond. But delocalizable lone pair will always be considered like a pi bond, which is going to help us in finding out the aromatic nature. And as guys, keeping all these facts in mind, let me summarize. You need a molecule to be cyclic. You need molecule to be planar. For molecule to be planar, all the atoms should be in sp2 hybridized state. So if it is about carbon, it should be either doubly bonded or cationic. If you see cationic carbon, it will always be sp2. Remember that. Boron with the 3 bonds. Or you may have sp2 hybridized heteroatom if its lone pair are delocalizable, right? But if you see any atom has a localized lone pair, then those lone pairs should not be counted in pi electrons. Guys, keeping this fact in mind, let's have a look at some example of aromatic compounds. Here we go. So is this molecule of benzene aromatic? Let's apply the criteria. What was the criteria? CPC, cyclic, planar, completely conjugated. Is it cyclic? Yes, it is. Is it planar? Well, all the atoms should be sp2. I can see all are doubly bonded, so it is planar. And complete conjugation. Let's say if I start from here, pi, alternate pi, alternate pi, alternate pi. From where I began, I reached there. So there is a complete conjugation. And how many pi electrons do you see? 3 pi electron, meaning total 3 pi bond, meaning total 6 pi electrons, which is a Halide number. So I will say yes, benzene is aromatic compound. Next one. This is nothing but cycloheptatrienyl cation, which is commonly called as tropylium ion. Well, is it aromatic? Cyclic? Yes, it is cyclic. Planar? Well, right from here up to here, all carbons being doubly bonded, they are going to be sp2 hybridized. And like I said, if any carbon you see cationic, it will always be sp2. So all sp2 meaning molecule is planar. And Let's check whether there's a complete conjugation or not. So pi bond in conjugation with pi bond, in conjugation with pi bond, in conjugation with vacant orbital, in conjugation with the pi bond. So there is complete conjugation of a pi bond. Due to complete conjugation, I will say first three criteria have been satisfied. And now, if you all see here, total pi bonds 1, 2 and 3. 3 pi bonds meaning 6 pi electrons. Presence of 6 pi electrons make this molecule aromatic in nature. Guys, just like compounds are aromatic, let me tell you, this aromaticity brings extra stability in a molecule. Likewise, there exists a concept called as anti-aromaticity. And if molecule is anti-aromatic, it is extremely unstable. So how do we identify whether compound is anti-aromatic? Well, the first three criteria remain same: cyclic, planar and completely conjugated. The fourth one changes. What is it? For molecule to be anti-aromatic, it should be cyclic, planar, completely conjugated. However, if they carry 4 n pi electrons, where value of n would be 1, 2, 3, so on and so forth. Meaning what? If you see pi electrons are in a multiple of 4, 8, 12, so on and so forth, provided the first three criteria are satisfied, you will say that molecule is anti-aromatic, and anti-aromatic molecules are highly unstable. So everybody, look at this molecule. We have got cyclobutadiene. Cyclobutadiene. In this molecule, it is certainly cyclic. I can also say this is planar because all the 4 atoms of the cyclic structure are in sp2 hybridized state. So it is planar. Complete conjugation, pi alternate pi alternate pi. From where you began, you are reaching to the same atoms again through pi bond. So it is completely conjugated, and 2 pi bond meaning it has got 4 pi electrons, which makes this molecule anti-aromatic in nature. So CpC 4 n pi electrons makes molecule anti-aromatic. Look here. Cyclopentadienyl cation. Well, in this molecule, is it cyclic? Yes, it is. Planar. This 4 carbon are sp2 because they're doubly bonded, and the cationic carbon which also makes that atom sp2, meaning this is planar and completely conjugated. And how many pi electrons we have got? 2 pi bonds meaning 4 pi electrons, which makes this molecule anti-aromatic. So guys, when molecule is aromatic, it is extremely stable. If it is anti-aromatic, it is extremely unstable. And if molecule is none of that, in general cases, we call them as non-aromatic molecules. So if you see, we have got molecule which is cyclic, but this is not going to be planar. Why? Because this carbon is in sp3 hybridized state. If it is sp3, obviously this is not going to be a planar. It will not acquire geometry of trigonal planar. So that's how the entire molecule will never be planar. Also, the conjugation is not complete. Pi alternate pi alternate pi. There is no further conjugation. So this molecule is neither satisfying the criteria of aromaticity or anti-aromaticity. So I'll refer this as non-aromatic compound. So aromatic extremely stable, anti-aromatic extremely unstable. So non-aromatic will be of intermediate stabilities of the other two. So guys, based on this, let's say we have got some example and we have been asked to identify whether given compounds are aromatic, anti-aromatic or non-aromatic. How will we do that? Let's apply the same criteria that we studied here. Look at this. Cyclic? Yes. Planar? Oh yes, this is planar as well because these two carbons are doubly bonded. This is cationic. All are sp2, so it is planar. Complete conjugation. Pi bond, alternate vacant orbital, alternate pi bond. So there is complete conjugation. And in 4n plus 2, 4n plus 2, if you put the value of n as 0, you will have 2 pi electrons. So this is satisfying Halide number containing 2 pi electrons, which makes this molecule aromatic. So I'll say this molecule is aromatic in nature. The next one, everyone here, this molecule is cyclic. Yes, cyclic. Is it planar? Well, 2 carbons are sp2, this carbon is sp3, but 3-membered ring is more or less planar only. So let's say this is planar, but there is no conjugation at all. Pi bond is not in conjugation with any of that. So this is neither aromatic nor anti-aromatic. So I will say this molecule is non-aromatic. Non-aromatic. Everybody here, last example, we have got some 5-membered cyclic structure with 2 pi bonds and boron atom here. Firstly, cyclic, yes it is. Planar, while 4 carbon right from here up to here are doubly bonded, so they are sp2. And I told you boron carrying 3 bond also is in sp2 hybridized state. That will make all the atoms in sp2, meaning this is planar for sure. Check conjugation. When this boron is in sp2 hybridized state, meaning there is one vacant p orbital for boron. So pi bond, alternate vacant orbital, alternate pi bond, which makes this molecule completely conjugated because of the vacant orbital. Conjugation will be completely in this ring, and total pi bonds, we have got 2 pi bond, meaning 4 pi electrons. Well, everyone, the moment we say it has got 4 pi electron, which is in a multiple of 4, that will make this molecule anti-aromatic in nature. So you see here we have got all the 3 types of compounds here. Let's see some more example. Fourth one, example of pyridine which we had taken. Let's take that again. Cyclic, yes. Planar, well, look at this lone pair. How do we say whether this is in sp2 or sp3 hybridized state? What I've told you, to check whether this lone pair are localized or delocalizable, imagine if you delocalize them, lone pair, alternate pi bond, if you delocalize them here, pi bond will go up. So this nitrogen will have one more pi bond here. So in that case, this nitrogen will be left with 2 sigma bond. 2 sigma bond meaning sp. So if this lone pair will delocalize, the nitrogen will demand geometry of linear geometry in cyclic structure not possible, meaning this lone pair will not delocalize. So they are localized lone pair. L meaning localized. If they are localized, I will count them like a lone pair only, right? So what is the hybridized state of nitrogen? 2 sigma bond plus 1 lone pair, 3 meaning sp2. So other all carbon are doubly bonded, so all are planar. So it is a cyclic, planar. And check complete conjugation. Pi, alternate pi, alternate pi, alternate pi. There is complete conjugation. And because lone pair are localized, we will not consider them as a pi bond. Those lone pair which are delocalizable, you will consider them for a pi bonds or as a pi electron. But these are not. So only 3 pi bond, which makes it 6 pi electron cloud. And then the moment we say that it is cyclic, planar, completely conjugated, and also following Halide number, I will say this molecule is aromatic in nature. So this is aromatic. Everyone, are you all there understanding, everyone? Okay. Excellent. Superb. Yes, Aman, absolutely correct. Absolutely correct. Yes, Riya, perfect. That is sp2. Okay. Well, guys, let's see 5th and 6th as well. Well, we have given a molecule which is certainly a cyclic one. Now to check the criteria of planarity, this 2 carbon and this 2 carbon, 4 carbons are doubly bonded, this is cationic. So all 5 carbons are doubly bonded, meaning they are sp2. What about nitrogen? Well, if you look at this nitrogen, they look like they are delocalizable. But we'll have to check first whether they are delocalizable or whether they are localized. So guys, if I delocalize it here, let's say if I delocalize like this. So we'll develop pi bond here. So nitrogen will have 1 sigma, 2nd sigma and 3rd sigma. Lone pair will become pi bond. 3 sigma meaning sp2. sp2 hybridized state is permissible in structure, which means this nitrogen's lone pair are delocalizable. Remember, these lone pair are delocalizable, so you're going to count them like a pi bond. So yes, nitrogen becoming sp2, which means it is planar. Complete conjugation. Well, lone alternate pi, alternate vacant, alternate pi, alternate lone. So all these lone pair and pi bond are completely in conjugation. So cyclic planar completely conjugated. And how many pi electrons do we have? 2 pi bonds straight away you see already. This lone pair, because they are delocalizable, they are also going to be counted as a pi bond because they are delocalizable. So 3 pi bond, meaning total 6 pi electrons. Presence of 6 pi electrons makes this molecule aromatic. So guys, even fifth structure is aromatic. How many of you could do it? Everyone? Okay. All right. Ria, sp3. No, it was sp2. Yes, Nilesh, perfect. This is aromatic. Rachna Behera. Yes, perfect. Perfect. Well, guys, here, let's look at the sixth one, the interesting example we have got here. So, what molecule is this? Firstly, let's understand that. We have got cyclobutynyl dication. Cyclobute, double bond meaning ene, and dication. So, this is cyclobutynyl dication. Okay. Now, how exactly do we figure out whether this is aromatic or not? First of all, is it cyclic? Yes, cyclic. To check the planarity criteria, these two carbons are sp2 being doubly bonded. These two are cationic carbons, so even they are sp2, so this is planar. Now guys, to check the complete conjugation, I want you all to pay attention here. As of now, pi bond alternate vacant orbital. Suppose if I delocalize it here, because flow of density will be from highly dense area to low density area. So pi bond is getting delocalized towards the cationic carbon. So I'll be getting resonating structure which will look like this. Now see, pi bond shifted here. This carbon as it is cationic, but this carbon, because lost one of its electron, is now becoming deficient. In this molecule, yet again I have got pi bond in conjugation with vacant orbital. If you delocalize it further, this will result in another resonating structure. You guys will have to keep drawing resonating structure unless you get the structure like the beginning structure, or there is no further conjugation. Okay. If pi bond getting delocalized here, this carbon was already cationic. Because this carbon lost this electron, this has now become cationic. Again, pi bond in conjugation with vacant orbital. So let us delocalize that as well. Upon delocalization, pi bond got delocalized here. So this cationic as it is, this is newly formed cationic carbon. Now guys, eventually if I delocalize pi bond in conjugation with vacant orbital, see, if you delocalize pi bond here, you're going to get the structure number 1. What does that indicate? That indicates pi bond is able to delocalize over all these 4 carbon atoms. Hence, I will say this molecule is cyclic planar, completely conjugated, and total we have got 2 pi electrons which are delocalizing completely, and 2 pi electron is a Halide number, which makes this molecule also aromatic in nature. Guys, how many of you could figure it out? How many of you could figure it out? Everyone? Okay. Okay, guys. Superb. So that's how any given molecule you can identify whether it is aromatic or anti-aromatic. Now everyone, the most important thing, like I said in the beginning, after learning a concept, we'll be seeing some of the previous year questions. So let me present one of the JEE advanced question you can see on your screen. This is 2013 JEE advanced question as an application of aromaticity. Everybody here? The question says, Among P, Q, R and S, the aromatic compounds is ours. So clearly it is a multiple choice question where multiple options could be correct. Okay. How do we find it out? Everyone, there have been given some molecule with AlCl3. Look. Very commonly you will see that in integer type question, they'll give you several aromatic compounds and along with some non-aromatic or anti-aromatic compound. And they'll ask you how many of them are aromatic. That is one way of asking question. Second way of asking question is like this, where the given compound directly need not be aromatic, but upon reaction with some of the reagent, it might turn into an aromatic compound. So you have to carry out that reaction and then check the product form whether it is aromatic or not. Like everyone, given molecule cyclopropanyl chloride, you can say, you're treating with AlCl3. So far in organic chemistry, whatever you have learned, you are aware that AlCl3 is a Lewis acid. Being Lewis acid, it can accept lone pair from another atom. So what Lewis acid does? Guys, hold on. Let me just take another color. So AlCl3 will accept lone pair from chlorine. So chlorine will acquire positive charge because it is losing electron. Aluminum will acquire negative charge. Eventually this bond will break, meaning Cl has lost from here in the form of Cl minus accepted by AlCl3. So AlCl3 came out as AlCl4 minus. But see what happened to this molecule. This molecule now became a 3-membered ring with the pi bond and a positive charge here. So now my question is, based on whatever we learned, just try and find out whether this molecule is aromatic or not. How do you do that? This molecule, is it cyclic? Yes, it is cyclic. Is it planar? Well, these two are doubly bonded carbon. This is cationic, meaning this is planar. Cyclic, planar. Pi bond in conjugation with vacant orbital in conjugation with the pi bond. So there is a complete conjugation. So cyclic, planar, completely conjugated, and 2 pi electrons present in the molecule, which makes this aromatic in nature. So P is certainly aromatic. Remember, this is aromatic compound. Let's come here. Q. We have to identify whether Q is aromatic or not. To understand that, look at this carbon. This carbon is sp3. I can see only 2 bonds. So how many more required? 2 more. Who satisfies those bonds? Hydrogen. Now, NaH indicate Na plus H minus. H minus is a very strong base. Being strong base, it will attack at the hydrogen atom. This H is lost to strong base because this H is acidic. Now guys, try to recall, when do you say compound is acidic? We say compound is acidic when the conjugate base is stable. So this H, I am calling it as acidic because after loss of H plus, this anion which will be formed, you will see sigma bond will come back and settle on this carbon. This anion is going to be extremely stable. If anion, meaning if conjugate base is stable, you will say that this compound is acidic. So what happened after loss of H plus? We got structure of Q can be represented like this. A 5-membered cyclic structure with the conjugation of a pi bond carrying 1 hydrogen atom and an electron pair on that atom. Is it? Yes, everyone? Now just simply find out whether or not this is aromatic. We have got cyclic structure and planar. 1, 2, 3, 4. Doubly bonded carbons are definitely sp2. But is this carbon sp2 or not? To check that, we have to check whether this lone pair are localized or delocalizable. If this lone pair are localized, then you will say 3 sigma plus 1 lone pair, meaning 4. So that will be sp3 hybridized atom. But if those lone pair are delocalizable, then this lone pair will delocalize, will form a pi bond, and that will become sp2. So to check whether or not those are delocalizable, the simple thing I have told you is lone pair, if you see in conjugation with the pi bond, let's delocalize them and see the structure which is formed. If you delocalize them, you will get formation of a pi bond. So this carbon will have only 3 sigma bond, 1, 2 and 3. The lone pair are going to be pi bond. 3 sigma bond meaning sp2. sp2 atom demands geometry to be trigonal planar, which is very much possible in cyclic structure. Hence, I will say these lone pair are delocalizable lone pair. If they delocalize, I'm not going to count them as a lone pair. I'm count them after delocalization. What are they becoming? They are becoming pi bond. So 2 pi bonds already exist. Lone pair is also becoming pi bond, meaning total 3 pi bond. So this is cyclic and planar because this carbon after delocalization becoming sp2. Rest all were already sp2. So cyclic, planar and complete conjugation. Lone, alternate pi, alternate lone. So complete conjugation and 3 pi bond, meaning 6 pi electrons, which makes this molecule also aromatic. So everyone, P is aromatic. Q is aromatic. Now what is left is R and S. Well, for R we'll need some space to work it out. So first let's do the simple one, that is S. In this S we have got HCl, that is H plus and Cl minus. In this molecule, the oxygen which is shown will certainly carry 2 lone pair, which makes it electron rich. So if lone pair attacks at H plus, what will happen? This 7-membered ring. So pi, alternate pi, and this now became double bond OH plus, right everyone? Now double bond OH plus indicate oxygen has become positively charged, so this pi bond will break towards oxygen to neutralize positive charge. So actually structure will look like C single bond OH and this carbon is going to be cationic. So I'm drawing that actual structure directly. How will it look like is OH and positive charge. Now everyone, I want you all to focus on this part of molecule. Think of tropylium cation. Wasn't it like this? It is cyclic. Planar because all carbon are either doubly bonded or cationic. Complete conjugation. Pi, alternate vacant. So complete conjugation and carrying 3 pi bond, meaning 6 pi electrons, which makes this molecule as well aromatic. So everyone, P, Q and S are certainly aromatic. Now let us talk about the R1. Okay, to check R1, we'll have to first find out the reaction between ammonium carbonate and this is diketone compound and heated at a higher temperature. Well, everyone, this is what they have given us. Look, this ammonium carbonate, NH4 twice CO3, we can put it this way. NH4, how can we write NH4? NH3H plus, right? And what we have got here is carbonate, CO3 2 minus. How many NH4 we have got? Twice. So this will be having twice. 2 ammonia, 2H plus. If you combine this, what is this becoming? H2CO3, carbonic acid, and we have got 2 ammonia. Let's take one of the ammonia out of that here. Now look, because everyone, because we have got H2CO3 which is carbonic acid, it's a source of H plus ion. So this lone pair of oxygen will attack at H plus and this will become OH plus. From where do we get this H plus? From carbonic acid. Now the moment this become OH plus, this pi bond will break towards oxygen to neutralize positive charge, which in turn making this carbon deficient. So immediately ammonia will attack here. So upon attack of ammonia, we now got this double bond O as it is. This now becomes single bond OH. There is one methyl and NH3 has attacked. And nitrogen will carry positive charge. Now everyone, in order to neutralize this positive charge, one of the hydrogen will be lost. That is what you call it as deprotonation. So this will become NH2. So this will be now converted to look here, double bond O. This OH and NH2, I'm interchanging their positions so that further reaction would be easy for us to represent. So we have got NH2 and this is the OH. Fine. Now because we have got NH2 here, this is nucleophilic in nature, and carbon and oxygen, O being more electronegative, this carbon will always have a delta plus charge. So lone pair of nitrogen will attack here. Pi bond will break to make it O minus. This O minus will accept H plus from either carbonic acid, or this NH2 after attack of lone pair anyway is going to lose H plus from here. So the H plus will be accepted by O. So you will get N bonding to this carbon. So 5-membered ring. 1, 2, 3, 4, 5. So let's put that. N carrying 1H and lone pair it got back because deprotonation took place. Now at this carbon there is one methyl and this is becoming C single bond O minus accepting H plus. So C single bond OH. So this carbon carrying methyl and OH. OH and methyl. Methyl even if you don't represent in bond line, that's fine. And at the other carbon also we have got OH and methyl. So let's put that as well. Fine. Now if you see the condition, we are further heating it also. So if you heat it further, it will undergo dehydration. So at this carbon we have got 2 H's, not to forget that. Now see, if you heat this further, what will happen? The carbon carrying OH, let's say it is alpha and this is beta. So from alpha OH will be lost, from beta H will be lost, sigma bond will shift here. Similarly here, from alpha carbon OH will be lost, from beta H will be lost, this sigma bond will further shift in here. So here will be getting double bond, alternate nitrogen carrying lone pair, alternate double bond. So the final product which they are referring it as R will look like this. So we have got N, alternate pi bonds, lone pair and H. Guys, this is nothing but R. Now let us refer to question whether or not this is aromatic in nature. So guys, is it aromatic? Well, you check yourself. This molecule is cyclic. Yes, it is cyclic. Cyclic. Is it planar? Well, 4 carbon which are doubly bonded are certainly sp2 hybridized. Nitrogen carrying lone pair, you have to check whether it is localized or delocalizable. If delocalizable, even that is going to be planar. So lone pair alternate pi bond. Imagine hypothetically if I delocalize it, I'm going to get pi bond here as well. So nitrogen will have 3 sigma bond left. 1, 2 and 3. 3 sigma is sp2. sp2 geometry is permissible. So this nitrogen is also sp2. So yes, all sp2 meaning planar. Conjugation, lone alternate pi, alternate lone. So there is a complete conjugation here. And because this lone pair are delocalizable, guys, I'm going to count them as a pi bond. So total pi bonds are 1, 2 and 3. 3 pi bond meaning 6 pi electron, which is nothing but the Huckel number. So all these conditions are these criteria are satisfied by the molecule. Hence even R will be referred as aromatic in nature. So guys, this JEE Advanced 2013 question had asked us among PQRS which are aromatic in nature. So yes, PQ, even R, just now we figured out even R is aromatic. So this was multiple choice question having more than one answer correct. So A, B, C and D, all of them are the correct choices. PQ, that is A, B, C and D, all options are absolutely correct. Right everyone, did you get it? See, to learn this kind of questions we had to learn so many concepts. So guys, to brief you, we were in general organic chemistry, and in this GOC what all we studied all the electronic effects, and then we studied aromaticity. We saw application of aromaticity. Now whatever electronic effect we have studied, all those electronic effects application we are going to learn very soon in order to find out the order of stabilities of carbocation, carbanion and checking or comparing the order of acidic strength and the basic strength of compound. So guys, quickly we are going to go over the application of electronic effect. Before which, one small concept which we have left, that is hyperconjugation. Well guys, in order to understand or learn the concept of hyperconjugation, we'll have to first justify that this is the correct order of this is not identifying the aromaticity. I'm just erasing this. Well, what we have to do is we have to justify the order of stabilities of this carbocation. Justify the order of the stability of following carbocation. Well guys, question is right in front of you. We have to justify this order of stability of carbocation. Giving you few seconds to give a thought on that and let me know. Well, let me just see your chat till then. Okay guys, so the question is we have to justify the order of stabilities of following carbocation. Let's see how exactly can we do that. Well, to justify this order, let's take one of the carbocation. Suppose I have taken this primary carbocation, ethyl carbocation here. Okay, if you observe this structure carefully, you will realize that there is sp2 hybridized carbon connected to sp3 hybridized carbon carrying at least one H, right? So if we have a carbon which itself is sp2 or at times even sp hybridized, if connected to sp3 hybridized carbon carrying at least one hydrogen atom attached to it, let me first tell you such carbon we refer it as alpha carbon atom. So the hydrogen atom present at such carbon we call it as alpha hydrogen. Guys, everyone here will have to speed up a bit, everybody here. So if you find there is sp3 hybridized carbon, that is alpha carbon carrying at least one hydrogen atom, then such carbon carrying alpha hydrogen connected via sigma bond pair, this bond breaks to release H plus and the sigma bond delocalizes completely into vacant orbital of adjacent cationic carbon. I repeat, in such cases when there is sp2 hybridized carbon adjacent to sp3 carbon carrying at least one hydrogen atom, so in such case hydrogen is lost as H plus, sigma bond completely delocalizes into vacant orbital of adjacent sp2 hybridized carbon. Sometimes such sp2 hybridized carbon could be even doubly bonded. So in that case the sigma bond, or rather the hybridized orbital of a sigma bond overlaps with the pi star, that is anti-bonding molecular orbital. Well, let's not get into that as of now, but that is one of the condition. So sigma bond if delocalizes, what you will see here, there will be development of carbon-carbon double bond and H will be lost as H plus. So you can see the positive charge has been dispersed from carbon to hydrogen, and whenever there is a dispersal of a charge, we say the energy of molecule lowers and molecule becomes more stable. So here, if this H can be lost as H plus, naturally the remaining two H's can also be lost as H plus. So just to distinguish these three hydrogen from each other, let's say I'm saying this is HA, this is HB, and this is HC. So as of now what happened, HA is lost as HA plus. Similarly, HB can be lost as HB plus, and similarly even HC can be lost as HC plus. In each case, if HB is lost, the sigma bond will shift here, you'll get pi bond here. If HC is lost, this sigma will shift here, you'll get pi bond over here. So this phenomena of a complete delocalization of a sigma bond pair into vacant orbital of adjacent sp2 hybridized carbon is what you call it as phenomena of a hyperconjugation. And the structure which you get as a result of hyperconjugation, we call it as hyperconjugating structures. So how many hyperconjugating structures we can get, that depends on how many alpha hydrogens we have. So as many number of alpha hydrogens we have got, those many number of hyperconjugating structure we get. So guys, further we say more the number of hyperconjugating structure, more the stability, because logically each time we are getting hyperconjugation, the positive charge is getting delocalized, that is dispersed, and the dispersal of charge always brings more stability to the molecule. So a phenomena of hyperconjugation will be observed anytime where you see sp2 hybridized carbon or even sp hybridized carbon connected to a saturated sp3 hybridized carbon carrying at least one hydrogen atom. So if we just come back to the previous question here, this is sp2 hybridized carbon. So any saturated carbon adjacent to sp2 is alpha. So even this is alpha, and even this is alpha. Each alpha is carrying 3 hydrogens. So total we have got 9 alpha H's. This is sp2, so adjacent is alpha, sp2 adjacent is alpha. 3 plus 3 total we have got 6 alpha H's. Whereas in case of ethyl carbocation, sp2 adjacent is sp3 carrying 3 alpha H's. Here in case of methyl carbocation, we just have got sp2 hybridized carbon. I don't see any alpha carbon atom. That indicates there is no alpha hydrogen present. And like we said, more the number of alpha hydrogen atoms, more the hyperconjugations, more the stability of molecule. Hence this is the correct order of stability of carbocation. Tertiary carbocation more stable, then secondary, then primary, and then methyl carbocation. So if we ever have got question where there is carbocation stability has to be compared, or alkene stability has to be compared, we can simply apply the phenomena of hyperconjugation to justify their stabilities. Just like we have got hyperconjugation, just like we have got inductive and mesomeric effect as plus I, plus M, minus M, we also have got hyperconjugation. One is your regular hyperconjugation where sigma bond delocalizes into vacant or towards pi bond. But if you see the flow of electron is in opposite direction from pi to sigma, we refer it as reverse hyperconjugation. And here is the example. Guys, imagine if we have got trichloropropene. You will see here we have got 3 chlorine connected to saturated carbon. Because all chlorine being electronegative, they'll withdraw electron toward itself, making this carbon deficient. The moment this carbon becomes deficient, the pi bond will delocalize towards that carbon to satisfy the deficiency, which in turn make chlorine leave or depart, because halogens are good living group. So chlorine has left. Once chlorine leaves from here, what will happen? This double bond will become single bond. You'll get positive charge here, and this pi bond have been delocalized here, and the chlorine has left in the form of Cl minus. Just the way this Cl has left in the form of Cl minus, remaining 2 chlorine can also leave in the form of Cl minus, which you can see here. You will get pi bond here and the positive charge. And likewise here as well, Cl minus, pi bond and positive charge. So here the flow of electron is not from sigma to pi bond. In hyperconjugation, what happens? Sigma bond delocalizes into either vacant orbital of sp2 hybridized or doubly bonded sp2. So general flow is from sigma to pi. Hence hyperconjugation is also referred as sigma pi conjugation. But what is happening here? Here pi bond is moving towards sigma. So the flow of density is in opposite direction. Hence we refer it as reverse hyperconjugation. Or you can simply call it as minus H, just like you say minus I and minus M. So everyone, we studied inductive effect and its type. We studied electromagnetic effect. We studied resonance effect and its type. We saw the application of resonance to learn the phenomena of aromaticity. and then we also studied the hyperconjugation. Now all these electronic effects can be studied together to understand its application or stabilization or destabilization of some of the cationic or anionic species. So everyone, what we have to learn now is the application of electronic effect towards stability or destabilization of some of the ion. So before you enter into questions straight away, few basic things I want you guys to learn and apply that accordingly. Okay, look here. If you look at this group other than hydroxy, you would say that this is benzyl carbocation. So everywhere I have got benzyl carbocation and I have to justify or I have to check the stability of carbocation. So imagine somehow at the carbon of benzene ring to which CH2 plus is attached, if at this carbon if you manage to get negative charge, so negative charge alternate vacant orbital, meaning it will stabilize the carbocation. So logically at the carbon carrying CH2 plus, if you get negative charge, it will stabilize the cation, and at the same carbon somehow if you get positive charge, it is going to destabilize the carbocation. So whether we get negative charge or positive charge at the carbon carrying CH2 plus depends upon the substituent present in the ring. So let us see how are this group contributing towards stability or destabilization of the carbocation. To understand that, everyone here, lone pair alternate pi bond. So what will happen? Resonance will take place. Lone pair delocalized here, pi bond move further, and this pi bond came on two atoms. So what charge will you get here? Negative charge. So this group is bringing negative charge at the carbon carrying cationic carbon. So it is stabilizing the carbocation. But this stabilization took place via electron donating effect. Donating meaning plus. Lone alternate pi is resonance effect. So I'll call this is plus M effect. So the benzyl carbocation is stabilized by plus M effect. So we understand that plus M effect is operating from the para position here. Now let's try and understand and the stability of carbocation, whether it is getting more stabilized or destabilized by OH present at the ortho position. So lone pair alternate pi bond, if you delocalize it further, pi bond will shift further. This will shift further, and at the carbon carrying cationic carbon you'll get negative charge here. So guys, what happened? Negative charge meaning it will stabilize. So even this carbocation got stabilized by plus M effect. That indicates mesomeric effect operates from ortho as well as para position. Now let's look at OH group present at the meta position. You can see lone pair are in conjugation with the pi bond, but if you delocalize it, pi bond will shift further, which will make this carbon pentavalent. So this will go further. Did I get any charge at the carbon carrying cationic carbon? No, I did not. Which means presence of OH group at the meta position is not stabilizing the carbocation. But on the other hand, oxygen being more electronegative than carbon, it is connected via sigma bond. So there is inductive effect operating. You see that? So OH is withdrawing electron. So at this carbon you will get deficiency. So another effect operating is minus I. The same minus I will also operate in case of OH present at para as well as at ortho. You can see here O withdrawing electron through sigma bond. So not only plus M operating, but there is minus I is also operating. But mesomeric effect is dominant or inductive, so we'll always consider the dominant effect. Same way here, oxygen is withdrawing electron and bringing positive charge here. So plus M is stabilizing the cation, minus I is destabilizing. But mesomeric being dominant, I'll consider plus M effect only. Guys, from this we learned that mesomeric effect, meaning resonance effect, operates only from ortho and para position, not from meta position. But inductive effect operates from ortho, meta as well as para position. Further, the mesomeric effect's impact is identical whether it is operating from ortho position or para position because it is distance independent. But inductive effect is distance dependent, meaning inductive effect from ortho position will be more prominent than meta than the para position. So point to be noted here, that is plus M and minus M will only operate from ortho and para position, whereas inductive effect, that is plus I and minus I, will operate from ortho, meta, as well as para position. So what we discussed here was plus M. Let's have a look at minus M here, everyone. How do you know that this is going to show minus M? Well, when we studied minus M, we studied first atom of a group. If multiple bond attached to more electronegative atom, pi bond will break towards oxygen, making nitrogen deficient, so it will withdraw electron. So this carbon will be deficient, so pi bond will shift here. Because this carbon lost this electron, you will get positive charge. There was already cation, so positive charge here, like charges will repel, energy of molecule will increase, so this will become less stable. So minus M effect is destabilizing the cation. Other than minus M, through sigma bond, it will also withdraw electron and again will bring positive charge. So it is destabilizing the cation also via minus I. So there is minus M and minus I both operating, but the dominant one is which one, everyone? Minus M effect. So I'll consider that minus M effect of nitro is destabilizing the carbocation. So the mesomeric effect, as we said, whether plus M or minus M will operate from ortho as well as from para. Para we saw. Let us check with the ortho position. Here, everyone, what do we see here? N double bond O. O more electronegative, it will withdraw electron. So nitrogen became deficient. Pi alternate deficiency, pi bond shifted here. So this will become deficient. Pi bond will shift further. So this is deficient. Pi bond will shift further and you'll get deficiency. Two like charges will repel, meaning it is getting destabilized. So minus M effect operated also from ortho position. That's what we mentioned here. But it is destabilizing. Similarly, N being more electronegative, it will also withdraw electron and destabilize the carbocation. So minus I is also operating, but dominant one is minus M. So just like plus M, even minus M operates from ortho as well as para. Ortho as well as para. That's what we mentioned here. But see from meta position whether it is operating or not. N double bond O, pi bond will break towards O. N became deficient. So this pi bond will shift here. So this became deficient. So pi alternate deficiency, this will shift here. Are we getting any charge here? No charge at the carbon carrying cationic carbon, which means the nitro group from meta position showing no impact via minus M effect. However, we must not forget that N being more electronegative, it is withdrawing electron, bringing positive charge here. So it is destabilizing via minus I effect. So we conclude that mesomeric effect operate from ortho and para position only, and it is distance independent. But inductive effect, whether plus I or minus I, operates from ortho, meta and para position, and it is distance dependent. The impact of inductive effect will be prominent if it is at ortho and will be minimum if it is at para position. Now guys, just like we studied plus M and minus M, let us also talk about plus H and minus H. Well, we are going to deal with this really very fast, so make sure that you pay attention. We have to study stability of carbocation. So there is methyl group here. You will see this is sp2 carbon connected to sp3 carrying at least one H. So this is your alpha carbon. So this is a perfect condition for hyperconjugation. In hyperconjugation, the flow of electron is from sigma bond to pi bond. That's why it is sigma pi conjugation. So sigma bond will delocalize here, pi bond will shift further. This will come back on the carbon carrying CH2. So see, sigma to pi bond is your regular hyperconjugation. Let's call it as plus H. So plus H effect is operating from para. At the same time, sp2 is more electronegative than sp3, so it will pull electron, meaning there is also electron donating inductive effect, meaning plus I is operating. But dominant one is plus H. So you'll consider plus H. From ortho position, sp3 adjacent to sp2, so sigma bond shifted here. This will shift further. So this pi bond has to go on to the atom carrying cationic carbon. Negative charge will stabilize the cation, meaning plus H is also operational from ortho position. And inductive effect. All alkyl groups shows electron donating inductive effect. So they will donate electron and stabilize the cation here. So there is plus I also operating, but dominant one is plus H. So from ortho and para, there is hyperconjugation operating just like mesomeric effect, right everyone? Well, so if you look at the meta position now here, in meta position you will see sp3 carbon adjacent to sp2. So let's say if we delocalize this sigma bond here, pi bond will shift further, making this carbon pentavalent. This will shift further here. I'm not getting any charge on the carbon carrying cationic carbon, which means the hyperconjugation effect is not operating from meta position, but electron donating inductive effect will certainly operate. So guys, just like we said, plus M and minus M, let me just summarize it once again. Plus M, minus M, and also plus H and minus H. Minus meaning reverse hyperconjugation. Okay. All these effects will operate from ortho and para position only, whereas inductive effect plus I and minus I will operate from ortho, meta and para position. Guys, I want you all to pay attention that mesomeric and hyperconjugation will only operate from ortho, para, whereas inductive effect will operate from all the position. Now whatever we have learned, just like hyperconjugation plus H, even reverse hyperconjugation will operate. I'll show it to you with one of the example. Look, sp2 carbon adjacent to sp3 carrying 3 withdrawing groups. So pi bond will shift here. So the flow of electron is from pi to sigma. So it is minus H. If this bond shifts here, this is deficient. This will shift further. This carbon is becoming deficient. Like charges meaning destabilizing. So reverse H is operating from para. Same will operate from ortho, but not from meta. Hence we said, just like plus H even minus H will operate only from ortho and para position. Do remember that. Right everyone? Okay. So what we have studied, let us apply that and just check the application. Before you enter into application, remember the intensity of electronic effect, meaning suppose in a given molecule there are several effects operating, one or two, then which effect to be considered as the dominant one? So always back bonding is the most dominant, whether it is contributing towards stability or destability, followed by bent orbital resonance, followed by aromaticity, then the simple resonance, and after simple resonance what comes? Hyperconjugation and inductive. As of now, the important ones for us is simple resonance, meaning what we studied just now, plus M minus M, hyperconjugation plus H, reverse H, and the inductive effect. So the dominant effect is going to be resonance, then hyperconjugation, and then inductive effect. Guys, using this, let us apply the all concept we have studied and see whether we are able to solve the questions or not. So we have to compare the order of stabilities of this carbocation. Now every time I am not going to draw structure. Just by looking at the group, I'll decide what it shows. So nitro group we studied, it shows minus M. All groups are at para, so I'm going to consider all the effect. Mesomeric, hyperconjugation as well as inductive. Minus M meaning it will withdraw electron. So at this carbon what I'm going to get? Plus charge. Plus meaning destabilizing the cation. Halogens, whenever you see halogens, I want you all to only consider minus I effect. As of now, let's take it as a data. For halides, you'll always consider minus I. So minus I will also withdraw electron, you will get positive charge here. It will destabilize the cation. Now we have got OMe. Oxygen carries 2 lone pair. So if the first atom of the group carries lone pair, what effect does it show? Plus M effect. Plus meaning donation. So at this carbon, electrons will be donated and you will get minus charge, which is stabilizing the carbocation. Methyl. First atom of group sp3 carbon carrying at least 1 H, meaning it will show plus H. Plus meaning donation. Donation will bring negative charge, so even this is stabilizing. So among all these options, second and third destabilizing the carbocation, fourth and fifth are stabilizing the carbocation. Right everyone? Everyone, are you understanding this or not? Yes. All right. Okay, Rajiv, Arshwardhini, excellent guys. Superb. So, second and third being destabilized because you see positive charge here. Fourth and fifth being stabilized. Now, if you compare the order of stability, fourth and fifth are the only ones which are stabilized. But between these two, fourth is stabilized via plus m. Like we said in the previous slide, this is more dominating than the plus h effect. So fourth is stabilized the most and then fifth. So order of stability will be fourth most stable followed by fifth. Second and third are destabilized. First at least not destabilized. So the next more stable is 1. Between 2 and 3, minus m is dominant effect. So the destabilization will also be more with minus m than minus I. So the least stable is 2. So relatively stable is 3. So 1, 3 and 2. That is your correct order of stability. Alright guys, so whatever we learned, we are just applying it here. Let me show you one more question. Now it is related to anion. Remember, if it is anion, positive charge here will stabilize it, negative charge will destabilize it. Okay. Again a nitro shows what effect? Minus m. Minus meaning withdrawal. Withdrawal will bring positive charge here. So nitro is stabilizing the carbon ion. Chlorine, I told you for halogen will always consider minus I. Minus meaning again withdrawal of electron, you will get positive charge. It is also stabilizing the benzyl carbon ion. OMe will show plus m effect because the first atom carrying 2 lone pair. Plus meaning donation. Donation will bring negative charge, so it is destabilizing the carbon ion. And the fifth one, sp3 carbon carrying at least 1 alpha H, so it is showing plus H. Plus meaning donation, so we'll be getting negative charge again here. Now, if this is benzyl carbon ion, then negative charges will destabilize it. So fourth and fifth is least stable. Second and third are most stable because the electron withdrawing group are pulling the negative charge, which is carrying out dispersal of a charge. Between 2 and 3, everyone, which is the dominant effect? Minus m is dominant over minus I. So the most stable is 2. Then 3, right? So if you write down the order, two and 3, and then at least one is not getting destabilized. Fourth and fifth are destabilized. So after 2 and 3, what comes is first. Between 4 and 5, 4 is destabilized by plus m, fifth is destabilized by plus h. Because mesomeric effect is dominant one, its destabilization will also be more. So fourth is destabilized the most. So relatively fifth is stable. And then comes is fourth. So everyone, that is the order of stabilities of carbon ion. Now let me present you the actual questions which were asked in the examination. On your screen, I have taken some phenols and carboxylic acid, substituted ones as well, and they're asking us to find out the order of acid extent using the same application which we studied just now. So guys, we are going to go and solve this question. Everyone, are you there? Okay. Well, someone asking, sir, for JEE advanced heterocyclic chemistry is important. Well, in some of the questions you may have a heterocyclic compound like in aromaticity. The special chapter of heterocyclic chemistry as such is not really what we study even in JEE advanced. Okay. With respect to question, if any such compound comes, then you'll have to apply the concept and get it done. Well, come back to this question. What is the correct order of acid extent? 2009 previous year question this is. Well guys, whenever you talk about order of acidic strength, when do we say compound is acidic? We say compound is acidic when the conjugate base is stable. So what are we going to do? All these acids will convert them into their conjugate bases. Converting them into their conjugate bases meaning assuming H plus is lost and it is becoming anion. So if H plus is lost, this is phenoxide ion or phenate ion. If H plus is lost, this is O minus. If H plus is lost from here, this is CO minus. H plus is lost, this is COO minus. All of this now are in the form of anion. Just now what we said, if all of them are anionic, then any group which will carry will bring positive charge here will stabilize the anion, negative charge will destabilize the anion. So more stable the anion, more acidic the corresponding acid will be. So you have to check now the substituent which are present, are they stabilizing the conjugate base or destabilizing? Because we said compound is acidic when the conjugate base is stable, and more stable the conjugate base, stronger the acid. So everyone, look here. If you look at first two compound, they are phenolic, next two are carboxylic acid. So anyways, carboxylic acid are more acidic because of their lesser pK value. So third and fourth are going to be more acidic for sure, and 1 and 2 are going to be least acidic. So let's not talk about 1 and 2 first. Compare between third and fourth. In case of fourth, the first atom of the group is sp3 carbon carrying at least 1 H, meaning this is going to show plus H. Plus meaning it will donate electron and it will bring negative charge here. Negative charge at this carbon will destabilize the anion. So if you compare third and fourth, fourth is being destabilized. On third, at least there is no group present which is destabilizing. So third is relatively more stable than 4. So 3 is going to be more stable than 4. So I will check for all this option. 3 more stable meaning stronger acid than 4. 3 greater than 4, you see that here. 3 greater than 4. Do you see any such option 3 greater than 4? And of course 1 and 2 are going to be less acidic than 3 and 4. So 3 followed by 4 has to be there. 3 followed by 4 doesn't exist here, ruled out. 3 followed by 4, it is here, but both of these are more acidic than 1 and 2. So even D is ruled out. And this is 4 greater than 3, so even this is ruled out. So straight away, by comparing third and fourth, I got the answer 3 greater than 4. But still, let's check with 1 and 2. Between 1 and 2, chlorine will show minus I effect. Minus meaning withdrawal. Withdrawal will bring positive charge. Positive charge here is stabilizing the anion. More stable the anion, meaning more stable the conjugate base, stronger the acid. 2 is greater than 1. 2 greater than 1. Hence, the right choice is option A. Everyone, did you get that? Everyone? Okay. Rakshita, it's gonna be A, not D. Okay, it's gonna be A. Yes, Harshavardhini, good to see you. Responding superb. 2 is stable than 1. Yes, 2 is stable than 1 via minus I. Yes, Rajiv, perfect. Alright, guys, chalo. Let's proceed with the next one. In the following compound, again, we have to find out the order of acidic strength. Now, for the first time, we have got a group present at meta position. We must not forget that minus M plus M minus H plus H does not operate from meta position. So in that case, we are going to only consider minus I. So far, all of them are phenol. To check their acidic strength, we'll have to convert all of them into their conjugate bases, meaning into their anions. And whoever's conjugate base will be more stable, meaning whichever anion is more stable, going to be the strongest acid. So let's say I removed H plus from all of them. And straight away converted them into their conjugate bases. Okay. Now check that which conjugate base is most stable. Everyone here. Nitro group is electron withdrawing mesomeric effect. So it is showing minus M because it is at para. And from para mesomeric effect operates. So withdrawal of electron through minus M will bring positive charge here. Positive charge here will stabilize the anion. So this is, yes, stable anion, meaning this compound is going to be acidic. Now we have got nitro, but it is present at meta position. From meta, we will only consider minus I effect. Minus via sigma bond will again bring positive charge, but the dispersal of this negative charge will be lesser than dispersal of this charge because it is via minus M and this is via minus M. Methyl group will show plus H effect as we referred earlier. Plus H will bring negative charge here, so it is destabilized. In case of phenol, the first one, there is no substituent, so this is neither stabilized nor destabilized anion. So if you compare all of them, third and fourth are stabilizing group to this corresponding phenate ion. But stabilization via nitro at para position is more. So fourth is the most acidic. Fourth is most. Followed by third. Second is being destabilized via plus H. So relatively one is more stable. So 4, third, 1 and 2. Where do you see this option, everyone? 4, third, 1 and 2. Here it is. Option D is the one which says 4, third, 1 and 2. So the right choice is option D. Alright, everyone. So guys, that was all about the general organic chemistry. We have covered the most important concept of GOC, that is electronic effect, including aromaticity. We saw its application in several questions along with the previous year question. Not to forget, we have also included question from JEE Advanced as well as JEE Main. So guys, that was all about GOC, and now we are going to proceed with the next subtopic, that is isomerism. But we will be taking a short break of 15 minutes and we'll be right back to learn this concept. So guys, enjoy your break for 15 minutes, relax a bit, and let's come back fresh to study the next one, that is isomerism and the further related subtopics. So guys, I'll see you in 15 minutes again. Thank you so much, everyone. Hello, hello, hello. Hello, everyone. Can you hear me? Guys, am I audible? Okay. Sahil, Suhana. All right, Aman, thank you so much. Hey, guys. Welcome back. Can you all see me? Can you all hear me now? Everyone? JEE aspirant 2023 Hindi bolo beta. This is the mode of communication of batch is English. That's why we are doing it. Okay. We'll have session in Hindi as well. Don't worry. But as of now, this session is in English, so we are communicating in that language. All right. Okay. Okay. You all can hear me. Great. Pika, Rachna, Siddharth, Janavi. Okay. Okay, Jayashree. No worries. Anyways, we are starting independent topic now, so you will be able to understand. Great. Rahul Ghosh. Superb. Everyone, chalo, let's get started now. Well, guys, so far in this complete organic chemistry in one shot, what we have studied is we finished general organic chemistry. We made sure that we included all the important electronic effects. We solved some question on that, including the previous year question from JEE Main as well as from JEE Advanced. We saw aromaticity and also the application of electronic effects, right? Now we are starting with the next important topic, that is isomerism. Well, guys, just to brief you about isomer before we actually start the concept that we have to cover, what are isomers? When you talk about this term isomer, isomers are nothing but compounds or two or more compounds having same molecular formula but different physical or chemical properties, or maybe both, then you call it as isomers, right? So whenever you will have two compounds which will share common molecular formula but will show different physical property or chemical properties, or maybe both, you call them as isomers of each other. Remember, isomerism is always a relationship, so there has to be at least two compounds which to whom you can refer them as isomers of each other. Now, these isomers we further classify into two categories: structural isomers and stereoisomer. When you talk about structural isomer, we say when two or more compound will have identical molecular formula but different structural formulae. So differences in the structure of two compounds arises due to difference in the connectivity of at least one atom. So in those two compounds, if you find at least one atom differing in their connectivities, you will say the structure of two compounds will differ. Hence, those will be called as structural isomers of each other. On the other hand, stereoisomers are those compounds which shares identical molecular formula as well as structural formulae, but the arrangement of atom in a space differs. Then you call such isomer as a stereoisomer. So, when it comes to stereoisomer, the molecular formula is going to remain same, as well as the connectivity of atom is going to remain same, but the arrangement of atom in a space, that is special arrangement, if differs, you call them as stereoisomers or space isomers. Guys, hold on. Okay, so structural isomers are of further type: chain isomer, positional, ring chain isomer, functional, metamers and tautomers. We'll cover some important part from here. Whereas stereoisomers, there are three types of stereoisomers which we study: geometrical and optical, which we call them as configurational isomers, and then comes is conformational isomers. So everyone, to begin with, let us talk about some structural isomers here, starting with chain isomers. Well, to understand chain isomers in the simplest way, look at this example first. Look at second example first. This is nothing but 1, 2, 3, 4 butanoic acid. This is 2-methyl propanoic acid, right? Everyone, when you see these two compounds, can I say these two have identical molecular formula? Of course, because number of carbon are 4. Here also number of carbon 4. Hydrogen 3 plus 2 5 plus 2 7 plus 1 8. C4H8, C4H8 and 2 oxygen atoms. So these two are sharing identical molecular formula C4H8 and O. Now, other than having identical molecular formula, we can also say the nature of functional loop is identical. So what all is identical? So what is same in these two compound is they have same molecular formula, they have same nature of functional loop. Sometimes you might find that the two compound will also have same nature of multiple bond, meaning double or triple bond. If one has a double bond, other will also have one double bond only. So they'll have same molecular formula, same functional loops, they'll have same nature of multiple bond as well. But what will be different is the nature of parent chain or a side chain. Like here in the first example, I have got parent chain of 4 carbon. Here I have got a parent chain of 3 carbon atom. So what will be different is nature of parent or side chain. So guys, simply how do we identify that the two compounds are chain isomer of each other? You look for those two compounds. If you find the two compounds shares same molecular formula, same nature of functional group, same nature of multiple bond, but different nature of parent chain or a side chain, you call them as chain isomer. For example, here I have got a molecule of 4 carbon atom, 8 hydrogen and 2 oxygen atom, both of this. Here parent chain is of 4 carbon, here parent chain is of 3 carbon. Here I have got one side chain, here we have no side chain at all. So nature of functional loop is say multiple bond. Well, as far as carbon-carbon bond is concerned, it is just saturated, so there is no multiple bond present. But the nature of parent chain is different. This is parent chain of 4 carbon, this is parent chain of 3 carbon. So this two will be regarded as chain isomer, Ci of each other. Similarly, if you look at the first example, this is nothing but N-butane, N-pentane, 5 carbon. This is 2-methyl pentane, or you can say isopentane as well. So the molecular formula is C5H12 in both cases. Molecular formula is same. There is no secondary suffix, meaning no functional present as such, but the nature of multiple bond, again both of them are just carrying single bond, so there is no multiple bond present. So molecular formula is same, all are singly bonded molecule, but the nature of parent chain is different. Here there is a parent chain of 5 carbon, here there is a parent chain of 4 carbon. So when these two differ in the nature of parent chain or side chain, I'll say these two are regarded as chain isomers of each other. Now guys, I'm going to share one simple trick to confirm that they are chain isomers of each other. The trick is what we call it as isomeric number. Isomeric number. By the way, this trick is only applicable to chain isomers, not to any other type of structural isomer. Isomeric number is represented as XY. Well, let me tell you, X stands for number of carbon atom in the parent chain, number of carbon in PC meaning parent chain, let's say, okay, and Y stand for number of side chain. Y stand for number of side chain, not the number of carbon atoms in the side chain. Okay, so if you find two molecules, like let's say here in the first example, if I want to find out XY number, so for N-pentane, XY number will be found out as number of carbon atom in the parent chain are 5. How many side chain? Y is number of side chain. I don't have any side chain here, so side chain 0. So isomeric number, XY number for first molecule is 50. Whereas for the second molecule, if you find out XY number of carbon in the parent chain are 4. And we have got one side chain, no matter how many carbon, one side chain. So XY number is 41. Because these two molecules differ in the XY number, which is isomeric number, I'll say these two are isomers of each other. Well, this is just a simple trick to identify the relation and only applicable to chain isomers. So each time if you feel that these are chain isomers, you can reconfirm them by applying the isomeric number method. The second example we have got, let's apply XY number here as well. Well guys, so number of carbon in the parent chain are 4. I don't see any side chain, so it is 40. In the next example, number of carbon in this parent chain are 3. 1, 2, 3. there is one side chain. So XY number is 3, 1. Because the isomeric number is different, I will say these two are chain isomers of each other. So for two molecules to be chain isomers, Ci of each other, the XY number must differ. Okay guys, let's see some more example for chain isomers. You can say this is 1-butene, this is isobutene. So in the first case, molecular formula C4H8, molecular formula C4H8 with one branch here. Nature of multiple bond is same, nature of multiple bond is also same. So molecular formula same, nature of multiple bond same, but the nature of parent chain is different. Parent chain of 4 carbon, parent chain of 3 carbon. So they are chain isomer, and you can compare their XY number simply as number of carbon in parent chain 4, there is no side chain, XY number 4, 0. Number of carbon atom in the parent chain 3, number of side chain 1, 3, 1. These two are differing in XY number, so they are Ci of each other. Let's have a look at this. Cyclohexane, this is methyl cyclopentane. XY number. Number of carbon in the parent chain 6, no side chain 0, 6, 0. For methyl cyclopentane, number of carbon in the parent chain are 5. Number of side chain, there is one side chain. So XY number is differing in these two molecules. I will say they are Ci of each other. The fifth example is interesting one, because so far all the example we studied, they were related to each other as a Ci of each other because of differences in the parent chain. But now the example that we are studying are differing in the nature of side chain. So everyone here, we have got ethyl cyclohexane and 1,2-dimethyl cyclohexane. So parent chain is of 6 carbon, parent chain is of 6 carbon. So parent chain is not different here, unlike other examples. Here side chain is of 2 carbon, here there are 2 side chain each containing 1 carbon atom. So if I apply XY number method here, number of carbon in the parent chain 6. How many side chain? I have got just one side chain, 6, 1. If you apply XY number method here, number of carbon in the main chain 6, and how many side chains? We have got 2 side chain. Now because the number of side chains are different here, you will say that these two are Ci of each other. So guys, that's how you can simply verify whether they are Ci or not. Next type here is positional isomers. Well, look at this first example. If I have to write IUPAC name of this compound, I would end up saying 1, 2, 3 and 4. That is butane 1-ol. Whereas in the second case it is 1, 2, 3 and 4. You will call this is butane 2-ol. So what do we learn here is molecular formula for both the compound is same. Molecular formula is same. Nature of functional group is same. Nature of functional group is same. Nature of multiple bond, in case if present, even that will be same. So molecular formula same, functional group same, nature of multiple bond same. If there are some substituent or side chain, those will also be same. But the position of all these things I said are going to be different in the same parent chain. So if two compounds have same molecular formula, same functional group, same multiple bond, same nature of substituent, but present at a different positions in the same parent chain, you call them as positional isomers. So see, you can see here functional group OH is present at carbon 1 in the 4 carbon chain. Here functional group OH is present at carbon number 2 in again 4 carbons chain. So the nature of parent chain is same, but the position of functional group being different, I will call they are pi of each others. Now let me tell you, isomeric number method or the trick that you applied is not valid here. That is only applicable for chain isomers. So guys, for any two molecule to be positional isomer of each other, they should have identical molecular formula, same functional group, multiple bond, substituent, any of that, but should be present at a different position. Let's have a look at the other example here. So 1, 2, 3 and 4. The best way to check the relation is write down IUPAC name. So 1, 2, 3 and 4. That's 1 butene and this is 2 butene. Because both of them have same nature of multiple bond, that is double bond, but the position of double bond being different, here it is at first, here it is present at second. So I will call them as what? Positional isomers of each other. You can see now we have got three molecules to be compared together. This is 1, 2 dimethyl cyclohexane. This is 1, 3 dimethyl cyclohexane. This is 1, 4 dimethyl cyclohexane. So the molecular formula is same. Nature of parent chain is same. Nature of side chains are also same. But the side chain are present at different position. 1, 2, 1, 3, 1, 4. So they are pi of each other. Positional isomers. Fourth, how would you end up writing IUPAC name? You will say this molecule is cyclohexa 1, 3 diene. Cyclohexa 1, 3 diene. And how about this? 1, 2, 3, 4, 5 and 6. You will say this is 1, 4. Hexa 1, 4 diene. So the position of two double bonds are different in this two structure, having the same nature of parent chain. So what are they? They are positional isomers because position is different. Here 1, 2 dichlorobenzene, 1, 3 dichlorobenzene, 1, 4 dichlorobenzene. Position of substituent, that is chlorine, is different in the same nature of parent chain. That makes this three molecule as positional isomers of each other. So guys, we studied something called as chain isomers, something called as positional isomers, right? Now suppose if we have been asked this question, draw all possible cyclic structure, not to forget. They have specified what they want. They are asking us to draw all possible cyclic isomer of C5H10 and establish relation among them. Then how do we do that? Firstly, C5H10. Look, your approach to solve this kind of question is, first, whatever number of carbon they have mentioned, draw cyclic chain of that many carbons. So with 5 carbons, we will have cyclopentane. Let's call this structure number 1. Now with 5 carbon, I can only have this one cyclic chain, cyclopentane. Now, if I decrease the number of carbon atom in cyclic chain, let's make it 4. So you'll need one more carbon in the form of branch. So methyl cyclobutane is another structure, right? Other than this, you may have 3 carbon cyclic chain cyclopropane. Now 2 more carbon left, so make that as a side chain. So ethyl cyclopropane is third structure. Now in the same cyclopropane, instead of having side chain of 2 carbon, you can have 2 side chain of 1 carbon each, meaning 1,1 dimethyl cyclopropane. So that is your structure number 4. And I may have one more possibility wherein cyclopropane, I'll take 2 individual side chain containing 1 carbon each, that is 1, 2 dimethyl cyclopropane. Now whether I take 2 methyl at the same carbon or at the whether I take 2 methyl at this 2 adjacent position or this 2 adjacent position, IUPAC wise they are going to be same only, right? That is 1, 2 dimethyl cyclopropane. So with the same molecular formula C5H10, how many structures are possible? 5. That is the first part of a question which we did. So you may have an integer type question also. The number of possible structures, possible cyclic structure for C5H10 would be how many? 5. Second part of question is establish the relation among them. Well, so to establish relation, what are we supposed to do is, let's say I'm relating 1 with 2, similarly 1 with 3, 1 with 4 and also 1 with 5. Okay, so I'm making sure that the first is related or compared with rest all. Likewise 2 has to be also related with rest all. So 2 compare with 3, 2 compare with 4, 2 to be compared with 5th. Likewise 3 to be compared with 4, 3 to be compared with 5, and finally we will be comparing 4th one with the 5th structure. Now guys, how do we compare this here? If you see first and second, first has 5 carbon chain, fourth has second has 4 carbon chain. So clearly nature of parent chain is different. Similarly, if you compare 1 with third, 5 carbon parent chain, 3 carbon parent chain. So first and third are also Ci of each other because nature of parent chain is different in all these cases. So if you compare one with any of this, you will see parent chain is certainly not of 5 carbon, parent chain either of 4 carbon or 3 carbon, which means because parent chain is different, all this relation, one is related to all of them as chain isomers. Ci meaning chain isomers. Okay. Now let's compare 2 with rest all. 2 is a 4 carbon parent chain. 3, 4, 5 are 3 carbon parent chain. So 4 carbon parent chain is certainly different than 3 carbon parent chain, meaning nature of parent chain being different. I will say 2 is related to rest all as chain isomers of each other. So these are also Ci. Now 3 has to be compared with 4th and 5th. Guys, 3 is a 3 carbon parent chain, 4 and 5 are also 3 carbon parent chain. So the nature of parent chain is not different. But if you look at the side chain, in the third side chain is of 2 carbon. Here there are 2 side chains of 1 carbon each, here as well as here. So 3 related to 4 as chain isomer because of differences in the side chain. Similarly, 3 is related to 5 as a chain isomer because of differences in the side chain. So 3 with 4 and 3 with 5 are also chain isomers of each other. Now 4th and 5th is little different than all previous relation because 4th and 5th both has 3 carbon parent chain and both of them have 1 carbon 2 side chain, methyl 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 methyl. So neither nature of parent chain nor nature of side chain is different. What is different is the position of those side chain. Here the side chain are present at 1, here the side chain are present at 2 different position. Because position of side chain differs, you will say they are pi of each other. So guys, that's how you may have a question by giving molecular formula and they'll ask you to find out possible cyclic structure, maybe even open chain structure, and they'll ask you to find a relation between them. Everyone, is that clear? Okay. All right, Priyani beta, that depends upon, let's see how the course flow is going, how much time is in our hand. If time permits, certainly we'll do that as well. Okay. Yes, Neha, perfect. Those are positional isomers. Correct. Okay guys, so what we learned here is about the isomeric relation of some of the structural isomers. Now let me take the discussion ahead with the stereo isomers. The first one we are going to learn here is geometrical isomers. Guys, I want you all to pay attention here. We studied that geometrical isomers are the type of stereoisomers. By definition, we say stereoisomers are the compound which have same molecular as well as structural formulae, but the arrangement of atom in a space differs, so you call them as stereoisomers of each other, right? So to understand that, let's have a look at this. This is 1,2 dichloroethene. 1,2 dichloroethene. Same here as well. Well, now when do we say that they are stereoisomer of each other? When the arrangement of atom in a space is different. Well, I can clearly see at this doubly bonded carbon, other than double bond, remaining 2 valencies are hydrogen and chlorine. Here as well, at doubly bonded carbon, remaining 2 valencies are hydrogen and chlorine. At the other doubly bonded carbon of first structure, remaining 2 valencies are again hydrogen and chlorine. Here as well, other than double bonds, the remaining 2 valencies are hydrogen and chlorine. Which means one thing is for sure, that the connectivity of none of the atom is different in this 2 structure. In both the cases, the connectivity of all the atom is same. If connectivity of all the atom is same, meaning we say structural formulae are also same. So these 2 compounds definitely have same molecular as well as structural formulae. But if you see the arrangement of atom, let's say I am referring chlorine atom. So in the first way of representation of molecule, both the chlorine atoms are present on the same side of double bond, whereas here those 2 chlorines are present on the opposite side of carbon-carbon double bond, which means the arrangement of atoms in a space is clearly different. But then question arises, how can we prove this, that the arrangement of atom in a space is different? Well, let's say using some of the modern techniques, somehow we managed to find out the distance between the 2 chlorine atom let's call this is D1. And we also found out the distance between the two chlorine atom in the second molecule as well. Let's call it D2. And when you compare distance D1 with D2, you will find that this distance is not identical. If distance between the two reference atom in the two structure is different, which means certainly the arrangement of atom in a space is also different. When the arrangement of atoms in a space differs, you call them as space isomer, or you call them as stereo isomers of each other. So now you may come up with an argument. So why are you saying that the distance is different? What if I interchange the position of chlorine and hydrogen? What if I interchange the position of chlorine and hydrogen? Chlorine will come down, H will go up. Then both chlorine will be having identical distance. Correct. But my question is it possible to interchange the position? Because in order to interchange the position, we will have to rotate the carbon-carbon double bond. But due to presence of pi bond between the two carbon atom, the rotation across this carbon-carbon double bond is not possible. The presence of pi electron cloud, which is formed due to lateral overlapping of p orbital, does not allow the free rotation to take place. If you apply more energy, then that pi bond might break, which means the rotation across carbon-carbon double bond is not possible. That kind of not possibility of rotation of carbon-carbon double bond is what you call it as restricted rotation of a pi bond. Restricted rotation of carbon-carbon single bond due to presence of pi bond. So you can say restricted rotation of carbon-carbon double bond in general. Because this rotation is restricted, you cannot interchange the position of chlorine and hydrogen, meaning position of all the atom in this molecule is fixed. Similarly, position of all the atoms in this molecule is fixed. That tells us the distance between the two chlorine atom is certainly going to be different if this is how they are arranged in a space. So such molecules which differ in their arrangement of atoms due to restricted rotation of carbon-carbon double bond, we call them as geometrical isomers. So what are geometrical isomers? A pair of stereoisomers. A pair of stereoisomer where arrangement of atom in a space is differing due to restricted rotation of carbon-carbon double bond is what you call it as geometrical isomer. But again, it need not be always carbon-carbon double bond responsible for existence of geometrical isomer. Well, there are several more types of systems which can allow molecule to exhibit GI, geometrical isomerism. What is that? There could be carbon-carbon double bond, carbon-nitrogen double bond, nitrogen-nitrogen double bond, as well as cyclic structure. Well, let me brief you this. When you talk about carbon-carbon double bond, meaning we are talking about alkenes, the example which we saw just now. When you talk about carbon nitrogen double bond, we talk about oximes, which means let's say if you have got molecule like this, so nitrogen carries lone pair and there is a presence of OH, and here the group present, let's say they are R1 and R2, or let's take hydrogen, that is also absolutely fine. So the presence of pi bond between carbon and nitrogen also brings the restricted rotation, and hence oxime can also show geometrical isomerism. Then there exists N double bond N, N double bond N meaning azo compounds. So azo compounds, this is how we represent. Valence you can satisfy with any group, let's say R1 and R2. So presence of nitrogen-nitrogen double bond is also responsible for geometrical isomerism. Likewise, cyclic structure. So if you take disubstituted compound, let's say at this carbon if I take A and B, and here if I take A and B, then I will say with respect to atom A, both the identical atoms are on the same side, or on this, both are above the plane of cyclic structure. You may have a arrangement of atom where if you put A down and B up, then in that case both A will be on the opposite side of a cyclic plane. So that is also responsible for the geometrical isomerism to be exhibited. So guys, molecules which are eligible to show geometrical isomerism, firstly, they need to have this kind of system. Either carbon-carbon double bond, carbon-nitrogen double bond like in oxime, nitrogen-nitrogen double bond like in azo compound, or in cyclic structure. But for such molecule to exhibit geometrical isomerism, the condition is that, the requirement is that at every doubly bonded atom, the two groups present must be different. Like in oxime, I've got carbon carrying alkyl and hydrogen, so these two groups are different. At nitrogen, although I've got only one OH group, but when atom carries lone pair, you don't look for atoms or a group of atom, you look for bond pair and lone pair. So bond pair and lone pair are also considered as just like two different groups having different priorities. Hence, those molecule also shows a geometrical isomerism. So guys, for molecule to exhibit geometrical isomerism, at every doubly bonded atom, whether carbon, nitrogen, or even cyclic structure, there should be two different groups present at every doubly bonded carbon. So condition is that there should be presence of two different groups at every doubly bonded atom. Alright guys, so if you find any molecule having two different groups present at every doubly bonded atom, that molecule will be eligible to show GI. For example, let's have a look at this. Now let's say we want to find out whether this molecule can exhibit geometrical isomerism or not, and if they do, then how are we going to name them? So let's say first they have given us 1-butene. Well, structurally 1-butene, how can we write it? CH3CH double bond CH3. Okay everyone, now what you have to check is at every doubly bonded carbon whether two groups are different or not. Like at this first doubly bonded carbon, two groups present are hydrogen and methyl. They are different. At other doubly bonded carbon as well, one is hydrogen, other is methyl. These two are also different. So it doesn't make any difference if the two same groups are repeated at other doubly bonded carbon. That is absolutely fine. But at a time when you're looking at a particular doubly bonded carbon, the two groups has to be different. Because at every doubly bonded carbon, two groups present being different, this molecule is eligible to show geometrical isomerism, and such carbon-carbon double bond at times is also referred as geometrical center, so you can call it as GC. So how will this molecule exist in two geometrical isomeric form is, look, I can write down this way. Carbon-carbon double bond. At the left hand side carbon, we have got hydrogen and methyl. We have got hydrogen and methyl. At other doubly bonded carbon, we have got hydrogen and methyl. Hydrogen and methyl, right? And I can have one more special arrangement of atoms which can be represented this way. On the left hand side doubly bonded carbon, I am keeping the two groups as it is. Hydrogen, methyl. But at the right hand side doubly bonded carbon, let's interchange hydrogen and methyl. Of course, we cannot interchange by rotating the carbon-carbon double bond, but let's say by some process only it is formed like that. So this is another possible structure. Now let's say your reference atom is hydrogen. Guys, in the first arrangement of atoms, both hydrogens are present on the same side of carbon-carbon double bond. So I will call such kind of isomer as cis geometrical isomer. When those two hydrogen atom or whatever is your reference atom, you could have taken even methyl, that is absolutely fine. Because two hydrogens are on the opposite side of carbon-carbon double bond, I am calling it as trans. So this is cis, this is trans. So across carbon-carbon double bond, if two identical, remember, if two identical atoms are present on the same side, you refer them as cis. If they're on the opposite side, you refer them as trans isomer. Guys, let's check out the second example, whether or not it can exhibit geometrical isomerism. We have got 3-hexene. Okay, CH3, CH2, CH double bond, CH, CH2 and CH3. So 1, 2, 3, 4, 5 and 6. So this is hex 3 in. Now at every doubly bonded carbon, two groups should be different. So there is H, there is ethyl. So these two are different. At other doubly bonded carbon there is H and there is ethyl. So at the other doubly bonded carbon also two groups being different, I will say both of this doubly bonded carbon carrying two different groups, so it is eligible to show geometrical isomers. And at both this doubly bonded carbon, at least one group has to be common. So let's say I'm considering hydrogen is common at both the doubly bonded carbon. So if I put both hydrogen on the same side of double bond, we'll call it cis. On the opposite side, we'll call it as trans. Likewise, the next one, 1-phenylethene. Well, everyone, 1-phenylethene. So carbon-carbon double bond, ethene. Let's satisfy the valency with H's. And at carbon number 1, I'm taking one of the group as phenyl. First of all, what do you think, everyone? Will it exhibit geometrical isomerism? Come on, I want your answer. Everyone, I'm expecting it from you. Come on. Will this molecule show geometrical isomerism? Let me see who answers. Okay. Well, at first doubly bonded carbon, two groups are hydrogen and phenyl. These two are different. So that is absolutely fine. But at other doubly bonded carbon, both atoms being identical, this molecule will not show geometrical isomerism. So such molecule will not exhibit geometrical isomerism because at one of the doubly bonded carbon, both groups are identical. See, if I compare these two H's, it appear like cis. But if I compare this two H's, it appear like trans. So within a same molecule, you cannot have two arrangement like that. Hence, at every doubly bonded carbon, the two groups has to be different. So guys, that's how you find out cis and trans isomer. Now, at time it happens that at every doubly bonded carbon, the two groups present will be different, but there will be no common atom. Like here, hydrogen is common. So I am able to say that this is cis because two identical atoms are on the same side. Here I am able to call it as trans because two identical atoms are on the opposite side of double bond. But imagine if there is no identical atom present, will we be in a position to call them cis and trans? No. But at the same time, at every doubly bonded carbon, if the two groups are different, then they are also exhibiting geometrical isomer. How do we name such compounds? So guys, the next one, such compounds are named as EZ, naming of geometrical isomer, where E stand for entgen, entgen. Entgen meaning away. Away meaning just the way we had in trans. In trans, two identical group has to be opposite. So the one which was trans, here I'm going to call it as E. So remember ET. ET for anything, any abbreviation, economic times. So T stand for trans. So whatever was trans, here I'm going to call it as E. Okay. What does that mean? I'll explain. Hold on for the time being. If you see isomer referred as Z, Z stand for Zusammen. Zusammen meaning together. So whatever was like cis, you're going to call it as Z in this case. And why do we need this kind of naming? Is look here. At this first doubly bonded carbon, I've got hydrogen and fluorine. At other doubly bonded carbon, I've got chlorine and bromine. So at every doubly bonded carbon, the two groups present are certainly different. Meaning this is definitely a potential geometrical center which should show geometrical isomers. So if this is showing geometrical isomers, how are we going to name it? Tell me, can I call it as either cis or trans? I cannot. Why? Because I don't see any common atom to say that two identical atoms are on the same side or are on the opposite side. For example, I don't see two hydrogen present on the same side or opposite, or I don't see, for that matter, two fluorine on the same side or opposite. So because there is no identical atom, we are not in position to name them as cis and trans. So in such case, where at every doubly bonded carbon two groups are different, but there is no group which is common, we don't name it as cis and trans, we name it as E and Z. How do we name it E and Z? Let's assume by some or the other way you are able to give priorities to these two groups present at the doubly bonded carbon somehow. Let's say I got to know that the priority of fluorine is 1 and priority of hydrogen is 2. We will learn how to give priority. At other doubly bonded carbon, bromine priority is 1, chlorine's priority is 2. Now, although I don't know, or rather I am not in a position to say two identical atoms are on the same side, but I am in a position to say that two identical priorities are on the same side of double bond. Same side of double bond meaning together. So I'm going to call it as Z isomer. Here, fluorine priority 1, hydrogen priority 2, bromine priority 1, chlorine priority 2. So you're comparing two groups at every doubly bonded carbon and deciding their priority. Now two identical priorities are on the opposite side, just like a trans, meaning here I'm going to call it as E isomer. So I'll refer this as E isomer. Now the big question remains is, how did we decide the priorities as 1 and 2? Well, the priorities of these two atoms can be simply decided by rules, set of 4 rules called as CIP sequence rule, where CIP are basically is an abbreviation from the initial of 3 scientists named Kahn, Ingold and Prelog. CIP, Kahn, Ingold and Prelog. So using this 4 sets of rule, we can decide the order of priorities of group. So the 4 sets of rule is number 1. Let's say if I've got a carbon-carbon double bond. Here first atom is hydrogen, here there is methyl, let's say. So what we do is we look for atom of first point of attachment to doubly bonded carbon, meaning to this doubly bonded carbon the first atom attached is hydrogen. Now although to this carbon there is methyl attached, the first atom is carbon itself. So you compare the atomic number of the first point of attachment. Because atomic number of carbon is higher than hydrogen, I will say this will receive priority 1, this will receive priority 2. So at every doubly bonded carbon, look for atom of first point of attachment. Whichever has a higher atomic number will be given higher priority. Suppose rule number 2 says at every doubly bonded carbon, if one is hydrogen and let's say other is its isotope. Now we are not able to assign priority based on atomic number because these are what? Isotopes of each other having identical atomic number. In that case, you decide the priority on the basis of mass number. So here the mass number is 2, here mass number is 1. Because deuterium has higher mass number, this is priority 1, this is priority 2. So if two atoms are isotopic with each other, the one with the higher mass number will give a higher priority than the other. Rule number 3, if first point of attachment is same, you go on to find out second point of attachment. What does that mean? Look. Let's see if I've got CH3 here. And here I've got CH2OH. Now if I apply the basic rules of assigning priority which we have studied so far, for this doubly bonded carbon, first point of attachment is carbon. Here also first point of attachment is carbon, and they are not isotopes also. So which means I won't be able to assign priority. So we apply rule number 3. Rule number 3 says if the first point of attachment is identical, go for second point of attachment. What does that mean? Well, if I simplify this methyl, I can put it this way. Carbon connected to 3 hydrogen. H, H and H. Well, here carbon carrying 2 H's and OH. See, what I'm trying to tell you is first point of attachment is identical in both the cases. Then you go for second point of attachment. After this carbon, second attachment is what? Either this H or this H. But we cannot certainly say that which H is first, which H is second, and which is third. So what you do, generally whatever three atoms are connected to that atom, you put them in the decreasing order of atomic number. Now because all three are H's, you can simply put H, 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 because all are identical. This is a set of three atoms. Here after carbon, the second atom could be either hydrogen or oxygen or hydrogen. So among this, which is of higher atomic number? Oxygen. So I wrote oxygen first, then hydrogen, and then hydrogen. Now you compare first atom of first set with first atom of second set. Do you see difference? Yes, I do. Oxygen is of higher atomic number. Hence the whole CH2H will be assigned priority 1 and this will be assigned priority 2. So guys, if the atom of first point of attachment is identical, go on to second point of attachment. If that is identical, go on to third point of attachment, so on and so forth until you find the difference. The next one, if any atom is doubly bonded, it is to be duplicated. If any atom is triply bonded, it is to be triplicated. What does that mean? Look here. Let's say one of the group is aldehydic, other is nitrile. How do we simplify? So this aldehyde can be simplified like this. First point of attachment is carbon. Now singly bonded atom, you write it down as it is. Now oxygen is doubly bonded, right? So I said doubly bonded atom to be duplicated, meaning I'll write oxygen twice. But tell me, in reality, do I have two oxygens? No, I have only one. So out of this two, one will be considered as real and other will be unreal or duplicate. So I assume this is real and this is unreal. Whichever is unreal atom, you put that in a parenthesis. Now, if oxygen was doubly bonded, so I wrote it twice. Similarly, carbon is also doubly bonded connected to oxygen. So even carbon should be written twice. So one carbon I have got, I need to write one more carbon, but that carbon should be written to a real oxygen, which is real. This was unreal. The one with the bracket, this is real. So put carbon here. But out of this two carbon, which is real carbon? This is the real because it is carrying H. So this is unreal. That's how doubly bonded atom is duplicated. See the triply bonded atom. You simplify like this. You got carbon. I don't have any atom singly bonded like H. So triply bonded atom to be triplicated, meaning I'm going to write it thrice. 1, 2, 3. N, N, and N. But in reality, do I have 3 N? No. I have only one real N. So out of 3, consider one as real N. Let's assume this is real N. Rest 2 are unreal or copies. If nitrogen was triply bonded, so we wrote it thrice. Even carbon is triply bonded to real N. So carbon should be thrice. So to real N, there should be 3 carbon. One is already there. This is second and this is third. But of 3 carbon, who is real? This is real. So rest are unreal. Basically, that's how you simplify. Now, how does it help? It helps this way. Look, because first point of attachment is carbon, you go for second point. Na? So after carbon, what is second point? O, O, O. Although it is unreal, you have to consider it. O, O, and O. So in the decreasing order of atomic number, the set of atom is OOH. After carbon, N, N, N. So this is going to be N, N, and N. So this helps us to find out the next priority atom. Simply, you don't have to even simplify that. By looking at this, you can simplify. How? After carbon, OOH, because it is doubly bonded. After carbon, N, N, N. That's how also you can do it. So guys, let's say if we have been given a question like this, what is it? Between 1 and 2, the Z isomer is. Which of this is a Z isomer? So what are you going to do? First, at every doubly bonded carbon, decide the priority. Look, to this carbon, I have got chlorine and oxygen. Chlorine atomic number 17, oxygen atomic number 8. So this is priority 1, this is priority 2. At other doubly bonded carbon, there is one iodine. And here first point of attachment is carbon. So we will compare carbon with iodine. Iodine is of higher atomic number. So that's priority 1. This is priority 2. Now compared to similar priority, 1 and 1 are on the opposite side. Like trans meaning ET. So this is E isomer, not our answer. Because we want what isomer? Z. Now look at the second one. To carbon, the first atom is chlorine. Now here, Although you see hydrogen is attached, but obviously this is CH2Cl. So to this carbon, point of first attachment is carbon, here it is chlorine. Chlorine a higher atomic number, priority 1, this is priority 2. If first point of attachment is identical, then you go for second, not otherwise. Here, doubly bonded connected to carbon, first point of attachment carbon, here also first point of attachment carbon. Now listen to me carefully. After this carbon, which are next 3 bonds, because one bond is utilized here, the next 3 bonds are carbon, carbon and hydrogen. So the groups are C, C, H. After this carbon, the remaining 3 bonds are, 2 are satisfied by hydrogen, 1 is satisfied by carbon, meaning C, H, H. Compare the first atom of set 1 with the set 2. This is carbon, this is carbon. We are not able to compare from carbon because both are identical. Then go for second. This is carbon, this is hydrogen. So carbon is higher priority. Hence this entire group will be given priority 1. This will be given priority 2. Now two identical priorities are on the same side, same meaning, like cis, meaning together, that is zosamin. Hence I'll say this isomer is Z isomer. So between 1 and 2, the Z isomer is 2. So your right choice is option B, which says only 2. Alright everyone, guys, are you all understanding or not? Aman, perfect. Khushi Chandekar, very good. Harshavardhini, superb. You have been consistent, very nice. Yes, Neha, excellent, excellent. Goki beta will be taking break, but not now, very soon, okay? You have to stay tuned. Well, that was all about the geometrical isomers, and now taking our discussion ahead with another important subtopic of isomerism, which is optical isomerism. Guys, before we actually learn optical isomers, we need to get introduced to these terms. Well, I'm sure you all have heard these terms: ordinary light, PPL, polarizer, polarimeter, optical activity and optically active compound, dextrorotatory compound, levorotatory compound. If these are of the same organic compound, you call them as enantiomers. Then mixture of these two in equimolar amount, racemic mixture. Then there's something called chiral carbon atom or asymmetric carbon atom. Well, the chiral atom need not be always carbon, it could be anything else as well. Followed by optical rotation and specific rotation. To understand all these terms, let me show you some diagrammatic representation which you have referred several times. Guys, have a look at this and try to recall something. I'll drink water till then. Yes, please have a look. Are we ready? Okay, guys, chalo. So the first representation you see, it says ordinary light. So what is the relation of ordinary light and the representation? Well, when you talk about ordinary light, we say it is a light whose radiation oscillates in all possible planes but perpendicular to the direction of its propagation, right? Here these arrows that you are seeing, which are represented in all possible direction, indicate that the radiations are going to oscillate in all possible planes. That's what this representation means. So ordinary light is the light whose radiation oscillates in all possible planes but perpendicular to the direction of its propagation is an ordinary light. So what we do is we allow ordinary light to pass through polarizer. Nichols prism is one of the polarizer. The role of polarizer or the function of polarizer is to allow only those radiation to pass through which will oscillate in only one plane. So let's say we use some polarizer like Nichols prism. We allowed ordinary light to pass through. We got a light whose radiations are now oscillating in only one plane, up and down, like you can see here. So such light having its radiation oscillating in only one plane, we call it as plane polarized light. So what we did, This plane polarized light we allowed to pass through or interact with solution of some organic compound like lactic acid, let's say, or glucose or many other such compound exist. So we took aqueous solution of lactic acid, we allowed plane polarized light to pass through it. When plane polarized light was passed through the solution of lactic acid, we will see the rotation or the angle of optical rotation will be changed either to the clockwise direction, meaning to the right, or to the anti-clockwise direction, meaning to the left. So this change in the angle of optical rotation which we have observed, we call it as the observed optical rotation. But this optical rotation, the change in the angle of optical rotation is observed when a plane polarized light was passed through the solution of lactic acid. So such compound like lactic acid which has ability to rotate the plane of plane polarized light either in a clockwise direction or in an anti-clockwise direction is what we refer it as the phenomena of optical activity, and the compound which can do so are called as optically active compound. So looking at this diagrammatic representation, we can certainly say that optically active compounds are capable of rotating the plane of PPL either in clockwise direction or in anti-clockwise direction. So if the organic compound's solution is capable of rotating the plane of PPL in a clockwise direction, we call it as dextro-rotatory compound, and if it rotates in the other way, that is anti-clockwise direction, you call it as levo-rotatory compound. So guys, dextro-rotatory and levo-rotatory compounds, or you can say dextro-rotatory and levo-rotatory isomers of the same compounds are called as optical isomers because these two molecules or the compounds will have same molecular as well as structural formulae, but ability to rotate the plane of plane polarized is different, equal in magnitude but opposite in direction. Such isomer we call them as optical isomer. So for example, if you talk about lactic acid, if you put that in a Fischer's projection, we show it like this. To remember simply, make first carbon COOH, carboxylic acid, last carbon CH3, because in Fischer's projection we make sure that the carbon chain is put vertically with highest oxidized group at the top of that carbon chain, and one of the valency we are satisfying by OH and other with H. This is what we call it as lactic acid. Well, when further research was done to identify why such lactic acid solution was capable of rotating the plane of plane polarized light, we observed one thing which was common in all other compounds which were also capable of showing this kind of optical rotation in most of the compound, and that was nothing but a presence of special type of carbon called as chiral carbon. Chiral carbon is generally represented by putting an asterisk on it. What is it? A saturated, a tetrahedral, meaning an sp3 hybridized carbon atom whose all the four valencies are satisfied by four different either monovalent atom or a group of atom. You call it as chiral carbon atom. So this is the lactic acid carrying one chiral carbon, and remember, if a given compound contains only one chiral carbon, then such compound will always be optically active. With two or more than two chiral carbon, it may or may not be optically active. How to find out optical activity? We are going to see that very soon. As of now, if this is lactic acid and if I take aqueous solution of this and pass plane polarized light, whether or not this compound rotate the plane of plane polarized light depends upon in which form it is present. So if I say I have got a dextro-rotatory compound, meaning if this compound is capable of rotating the plane of plane polarized to the right, I'm going to call it as dextroisomer. It is symbolized as D or plus, and then you can write its name as lactic acid. But dear student, whether it is dextro or levo, that we cannot find out just by looking at the structure. We will have to literally take this compound, make a solution and pass plane polarized light and observe that in a polarimeter. So polarimeter is a device which basically tells us the change in the angle of optical rotation. So if I say this is D-lactic acid, meaning dextrolactic acid, then question is how L-lactic acid looks like. Well, let me tell you, whichever compound existing in D form, that is dextroisomer, its levoisomer will always be a mirror image of dextro. And that's why if the first one I'm calling it as D isomer, that is D lactic acid, this one I'm going to call it as L or minus lactic acid. I want you guys to understand one thing. From a given structure, we can never say whether compound is dextro or levo. It is purely an experimental observation to say whether compound is dextro or levo. So, if one of the compound, I am saying if this isomer is dextro, then I can say its mirror image will be levo. So, if and then is very important, because just by looking at the structure, we will never be in position to say whether this is dextro or levo isomer. Now guys, let's come back to the very important concept that we were talking about. If a given compound contains only one chiral carbon, we said it is always going to be an optically active compound. With two or more than two chiral carbon, it may or may not be optically active. So how do we identify whether a given compound is optically active or not? Well, a chiral carbon, sometimes also referred as asymmetric carbon, represented by putting an asterisk on that carbon. So just having asymmetric carbon or chiral carbon does not make compound optically active. For a compound to be optically active, for a molecule to be optically active, meaning for a molecule to be chiral, the whole molecule has to be asymmetric. For a molecule to be optically active, only presence of asymmetric carbon won't work. The whole molecule has to be asymmetric. So question arises, how do we know the whole molecule is asymmetric? Well, we will say a whole molecule is asymmetric if the mirror image of molecule is non-superimposable upon its object. If you take a compound and take a mirror image of that, if that mirror image is non-superimposable upon its object, you say compound is whole asymmetric, then you say the compound is whole chiral or optically active. But not always it is possible to compare the mirror images and say or to tell whether those are non-superimposable upon each other or not. So whether or not given molecules mirror image are non-superimposable upon that can be simply found out by applying the symmetry element criteria. So if a given molecule or whatever compound is given to you, if it does not have any of the element of symmetry, a molecule should not possess. If molecule does not possess any of the following element of symmetry, then you will say the molecule is optically active. What does this mean, guys? For a molecule to be optically active or molecule to be chiral, only chiral carbon is not sufficient. The whole molecule should be asymmetric. Whether or not whole molecule is asymmetric as a whole, we can check by checking the non-superimposability of mirror image. But not always we are able to compare the mirror images and to tell whether they are non-superimposable upon not. So eventually what we say, the mirror images will be non-superimposable if the molecule does not possess the following element of symmetry criteria. So which are the element of symmetries? We simply check plane of symmetry and center of symmetry. So if your molecule does not possess plane of symmetry or element or center of symmetry, in that case you can certainly say that the molecule as a whole going to be asymmetric because it is not following any symmetry criteria. So if this molecule as a whole is asymmetric, you can say the compound is chiral or optically active. So guys, presence of one chiral carbon will make compound always optically active. But with two or more than two chiral carbon, you cannot say whether it is optically active or not. You will simply check whether molecule contains plane of symmetry or center of symmetry or not. If molecule does not contain any of this symmetry, then you will say molecule is optically active. So long story short, in simple words, for a molecule to be optically active, we'll check two things. Number one, check first whether it contains only one chiral carbon or not. If it contains one chiral carbon, it will always be optically active. If you see molecule does not contain chiral carbon or has more than one chiral carbon, apply this symmetry element criteria. If it does not contain any of this, then again the molecule is going to be optically active. Now guys, based on what we have learned, let's have a look at some more important relationships in this optical activity. Well, if you see the molecule that we have mentioned here, these molecules are represented in the Fischer's projection. Okay. When you represent molecule in the Fischer's projection, at times it becomes easier for us to compare their images. So these images can exist in different optical isomeric form, which are called either enantiomers, diastereomers, or mesocompound. Let's try and understand them. Okay. Well, everyone here, well, what is this first molecule? This is nothing but 1, 2, 3, 4, 5, 2, 3 dibromo pentane. 1, 2, 3, 4, 5, 2, 3 dibromo pentane, again 2, 3 dibromo pentane, again 2, 3 dibromo pentane, and that is tartaric acid. So first three are a different arrangement of molecules in a space, but the compound is still the same. Let's find out the relation between all of them. Well, guys, look at this first molecule. Is this carbon chiral? Yes, it is. Is this carbon chiral? Yes, it is. But like I said, with two chiral carbon, it need not be always optically active. So check whether there is a plane of symmetry. Guys, what if I put an imaginary plane like this? Is this imaginary plane cutting the molecule into two equal half? No, it is not. Because up here I've got methyl, here I've got ethyl. So these two parts are not a mirror images of each other. Meaning in this molecule there is no mirror plane of symmetry existing. If there is no symmetry, meaning this is optically active. So I will say this is optically active isomer of 2,3 dibromopentane. Now let's come to the second. Even this is 2,3 dibromopentane. Again we have got chiral carbon, but there is no plane of symmetry. Even if you consider this as imaginary plane, these two parts are not mirror images. This is methyl, this is ethyl. So there is no plane of symmetry. If there is no element of symmetry, which means this is optically active. So even this is optically active isomer of 2,3 dibromobutane, just like that. But everyone, what if I compare these two? If I compare these two, can I say these two are related to each other as a mirror images? Yes, they are. So structure number 1 and structure number 2 both are optically active isomer of the same compound 2, 3 dibromobutane, and they are also related to each other as a mirror images. So I will say a pair of optically active isomeric compound of the same compound, pair of optically active isomer of the same compound which are mirror images of each other, we call it as enantiomers. So guys, I'll say structure number 1 and structure number 2 is a pair of enantiomer, a pair of optically active isomer of the same compound which are mirror images of each other. You call it as pair of enantiomer. Now let's compare 2 with 3. Well, chiral carbon, but there is no mirror plane of symmetry. Now though, other than methyl and ethyl, even Br is not like an image with H. So this is also optically active because even this does not have a plane of symmetry. So an optically active isomer of again 2, 3 dibromobutane. Even this is optically active isomer of 2, 3 dibromobutane. But are 2 and 3 related to each other as a mirror image? just like 1 and 2. Check. Against H you have got H, again H you have got Br. So even if you consider mirror here imaginary, these two are not going to be mirror images of each other. What does that mean? Although this is optically active isomer of the same compound like this, that is 2,3-dibromopentane, they are not a mirror images. So I will say a pair of stereoisomer. Now I am not referring them as pair of optically active isomer. I am referring them as pair of stereoisomer which are non-mirror images of each other. A pair of stereoisomer which are related to each other as a non-mirror images, we call them as distereoisomers. Distereoisomers or distereomers you can say. So everyone, structure number 2 and structure number 3 will be related to each other as a pair of distereomer. And not only this pair, now I want you guys to compare first with third. Compare first with third. 2,3-dibromopentane, 2,3-dibromopentane. Are first and third related to each other as mirror image? Against Br, I have got H. Certainly they are not a mirror image. So first and third are also pair of stereoisomers, but not a mirror images of each other. Because they are not a mirror images of each other, even they are distereomers. So other than second, third, even first and third are distereomeric pair of each other. And now here comes the final one, tartaric acid. Well, the tartaric acid I have represented in such a way where this is chiral carbon, this is chiral carbon. But imagine if I pass an imaginary plane like this. So this imaginary plane is cutting the molecule into two equal halves, isn't it? So when such plane divides the molecule into two equal halves, I will say this molecule has plane of symmetry symbolized as sigma. And when molecule has a plane of symmetry, meaning molecule as a whole is not asymmetric. So this is not optically active, this is optically inactive. So compound containing two chiral carbon but yet optically inactive due to presence of mirror plane of symmetry is what we refer it as meso compound. So we refer this as mesotartaric acid. That's what we were talking about earlier. With one chiral carbon, compound will always be optically active. With two or more than two chiral carbon, it may or may not be optically active, and meso is the best example of that. So guys, we studied three types of isomeric relation. Number one is enantiomer. What are enantiomer? Pair of optically active isomer of the same compound which are mirror images. Second is diastereomer. What are diastereomer? Pair of stereoisomer which are non-mirror images are diastereomer. And what is meso? Compound containing two chiral carbon but yet optically inactive due to mirror plane of symmetry. So due to internal compensation, it is going to be optically inactive compounds. Now guys, we studied something called enantiomer, we studied something called diastereomer, and we studied something called as meso. See, studying this all type of isomeric relationship was easier for me because I was able to compare their structure because they were put in the simplest form of representation called as Fischer's projection. Which means to find out the isomeric relation among the molecule becomes easier if we put them in the form of the Fischer's projection. Hence, any question given to us, we will always make sure that whatever projection they are given, the structures, whether they are given in Sohor's projection, whether the molecules are given in Newman projection, I will always try to first convert them into Fischer's projection. Once you put them in Fischer's projection, comparing whether they are mirror images or non-mirror images or meso becomes easier for us. So keeping this fact in mind, well, these are the terms which we studied just now. Let's say now we have been asked to find out absolute configuration of this molecule. Well, there exists absolute configuration. One type of absolute configuration is small d and small a, dextro and levo. Absolute configuration is something which is independent or it is not related to the reference configuration. So D and L, small d and L, as well as capital R and S, meaning rectus and sinister, is what you call it as the absolute configuration. How do you find out this RS configuration? Well, to find out RS configuration, we again take a help of CIP sequence tool and we assign priority to the 4 groups present at the chiral carbon atom. For example, suppose if I take this structure again here, everyone. Let's say this is the structure given to us. Here we have got COOH, C double bond OOH. To the right we have got OH. To the left we have got Cl. Down here we have got methyl. Then we have got hydrogen atom here and here as well. Okay. Now first identify the chiral carbon atom. Well, look, this is chiral and even this is chiral. So you're going to assign configuration to the chiral carbon only. So if you do IUPAC numbering, this is carbon number 1, this is carbon number 2, this is carbon number 3, carbon number 4. So we have got 2 chiral carbon, number 2 and number 3. So now we have to find out the absolute configuration at carbon 2 and 3, whether this is R or S, similarly whether this is R or S. Well, when you talk about R stands for rectus. Rectus meaning to the right. And S stand for sinister. Sinister meaning to the left. So what we do, let me just brief you simply. Firstly, what we do is we look at the chiral carbon atom and what are groups present here, A, B, C and D. We assign priority to this group. So let's say using CIP sequence rule, we give some priority. Let's say this was priority 1, this was priority 2, this is priority 3 and this is priority number 4. Okay, using CIP sequence rule which you have learnt. Once you assign the priority, we always make sure in Fisher's projection the lowest priority, meaning the priority number 4, is always put on a vertical bond, either up or down. Once you have assigned the priority, we always make sure that the lowest priority, meaning the 4th priority group, is put on a vertical bond either up or down. Why so? Because this Fisher's projection is a conversion or a projection of a 3-dimensional molecule where the bonds which are present on the horizontal lines are the ones coming outside the plane of paper, and the groups which are present on the vertical line are the group which are going inside the plane of paper. Inside meaning away from the observer. So the rule says, or the convention says, the 4th priority group should always go away from the viewer or the observer. So the group which are going away are either vertically down or vertically up. Hence we always make sure that the 4th priority group should be always up or down. If it is not up or down, then we have to bring it either up or down and then assign the name. Let's say in this molecule 4th priority is already on a vertical bond. If it is already on the vertical bond, you ignore the 4th and read the other priority 1, 2 and 3. When you read the other priority group, your eye move in anti-clockwise direction 1, 2 and 3. Anti-clockwise direction meaning to the left. So I will assign the designation as S. I will say this molecule as S absolute designation. If 1, 2, 3 designation, if 1, 2, 3 priorities would have moved in the direction where if your eye would have moved in a clockwise direction, you would have called it as R. Okay. Well, have a look at this. So I'm going to assign the priority. So at this chiral carbon, first point of attachment O, this is carbon, hydrogen, this is carbon. So among all the atom, oxygen is always highest priority because oxygen has higher atomic number than carbon. Now from this carbon, this was again a carbon. So first point of attachment carbon, first point of attachment carbon. But after carbon, next 3 groups are OOO, doubly bonded. I have taught you this. After this carbon, next are ClCH. So for this whole group, for whole this group, because this is the 4th priority, ClCH. Certainly ClCH, if you compare chlorine with oxygen, chlorine is higher atomic number. So this whole group will be given priority 2. Chlorine, oxygen will be given priority 3. Hydrogen will be given priority 4. Okay. Now, once you know that you have assigned the priority, you always want fourth group should be on a vertical line. Do we have fourth group on a vertical line? No. So what I said, you have to bring fourth group on a vertical line. But even without bringing fourth group on a vertical line, you can still find out RS designation. See, your answer is going to be either R or S. Either going to be R or S, meaning 50% possibility to the R and 50% possibility to S. So if your fourth is not on a vertical line, still if you look at other groups, suppose if I avoid fourth, although it is not on a vertical line, 1, 2 and 3, your eye is moving in a clockwise direction. So assuming fourth priority at a position where it should not be, if you find the configuration of molecule is clockwise, meaning it is R, which means certainly your answer is not going to be R, it is going to be other than R. Why? Because we got answer as R when the fourth priority is not on a vertical position. So if fourth is going to be on a vertical position, then the answer is going to be other than what it is right now. So when fourth is on a horizontal line, it is showing R, meaning actual designation at second carbon is S. So at second, the designation is S. Similarly, come down to this third carbon now. I'm using other color code, orange one. For this carbon, first point of attachment chlorine, carbon, hydrogen and carbon. So chlorine is highest priority, number 1. Down here I've got carbon, after carbon HHH. Up here after carbon, the next second point of attachment is oxygen, carbon and H. Oxygen, carbon and H. Meaning certainly up here this is second priority, this is third and this is fourth. Now see, again fourth is not at the place where we want it. So let us assume that fourth, wherever it is, if I see the answer 1, 2, 3, I is moving as 1, 2, 3 anti-clockwise direction, meaning if our answer is turning out to be S, meaning in reality answer is not S, it is R. Right everyone? 1, 2 and 3 moving anti-clockwise, up here like S, but it is not S, it is R. So at third, the designation is R. Guys, let me check once again. 1, carbon, carbon, OOO, Cl, CH. So Cl is priority. So 1, 2, 3, R, but it is S. Correct. So 2S and 3R. 2S, 3R. Where do you see that option? Here it is. 2S and 3R. So guys, that's how using CIP sequence rule we assign the priority. Once you have assigned the priority, you find out the answer. And now we are going to proceed with an interesting example, one of the previous year question, which is right here. Which of the following given statement about MNOP are right with respect to M? With respect to M, you have to find out relation of all of this. Guys, let me tell you, this is multiple option correct 2012 JEE advanced question. Well, I'm giving you 2S3R. 2S3R. Helen, 2S3R. How come? Let me check again. How come 2S3R? Yes, 2S3R. Correct, correct. 2S3R is absolutely correct. Even we have got the same answer. Perfect. Yes, guys, here. Well, so they have given M, N and O in the form of Sohor's projection. P and Q they have given in the form of Newman projection. And they are asking us to find out relation of M along with all of them. So just now we studied how to find out whether they are enantiomer, how to find out their non-mirror, meaning diastereomer, so on and so forth. So guys, in order to find out the relation among those isomer, it becomes always easier when the given structures are in the Fisher's projection, is what we have studied. So our job will be to convert them all into Fisher's projection. Now how do we do that? Let me tell you. Look, everyone, let's assume our requirement is to get Fisher's projection like this. Okay, whatever group you call it. Let's say this is A, B, C, D, E and F. Well, this is the molecule carrying 2 chiral carbon atom, or Fischer's projection carrying 2 chiral carbon atom. If you have got Fischer's projection carrying 1 chiral carbon atom, it appears like this. Let's say A, B, C and D. Okay. This Fischer's projection is interpretation of this kind of 3D structure. This is A, B, C and D. So let me tell you, what we have drawn here is equivalent of this. Or rather, this three-dimensional structure is converted into Fischer's projection in this way. What does this tells you? This tells us B and D are the groups coming outside the plane of paper, like this, towards observer. So those are to be always put on a horizontal line. A and C, which are going away, going inside the plane of paper, meaning going away from the viewer, has to be always put on a vertical line, which is A and C. So this three-dimensional structure will always be written in the Fischer's projection like this if there is 1 chiral carbon. And I say such arrangement is a set of 2, 2. Set of 2, 2 as in what? 2 on a vertical line going inside the plane of paper, 2 on a horizontal line, meaning coming outside the plane of paper. Meaning, in simple words, if 2 are in one of the plane, the other 2 are in the opposite plane. As simple as that. If 2 are going inside, other 2 are coming outside. If this is a set of 2 and 2, guys, I will say this is a set of 2, 4. Why 2, 4? Because there are 2 groups on a vertical line. Like we had a 2, here we have got 2. But there are 4 groups on a horizontal line. B, F, C, E. Here we had only 2. That's why it was 2, 2. Now this is 2, 4. So, in case of a chiral compound containing 2 chiral carbon atom, putting them in the Fischer's projection, meaning in other words, bringing the groups in the form of set of 2, 4. 2 meaning the one which are on a vertical line, 4 are the ones which are on the horizontal line. So, in any case, if molecule is given in the Sohor's projection, we'll always try to convert that Sohor's into set of 2, 4. What does that mean? Look here. Let's say we have been given some Sohor's like this. Okay, guys, hold on. And here at this carbon, okay, randomly we have been given this molecule and we have been asked to convert this into Fischer's projection. Look, when you compare this molecule in the Sohor's projection, you have to consider one imaginary plane. So let's say this is the imaginary plane I am considering. Okay. And imagine if someone is observing this molecule from here, from the top view. So C, E and B are above the plane because this dotted line is the plane which we are assuming imaginary. So C, E and B are above the plane. D, F, A are below the plane. So as of now, the groups are in a set of 3, 3. 3 above the plane, 3 below the plane. Meaning 3 in one plane, other 3 in opposite plane. This is not we need. What we need is set of 2, 4. If 2 are in one plane, other 4 are in different plane. Then only we will be able to convert this Sohor's into Fischer's projection. So what we did is, we tried to convert this molecule this way. Look here, everyone. Now if I consider imaginary plane again, and if you observe the molecule from this top view from here, how many are coming towards you? 1, 2, 3, 4. How many are going away from you, meaning opposite plane? 1 and 2. Now we have got a molecule in a set of 2, 4, isn't it? So we'll always try to convert this kind of Sohor's into this kind of Sohor's, so that conversion of such Sohor's into Fishers become easier. Further, when you write Fisher's projection, there are some guidelines that we have to keep in mind. If you remember, when we wrote a structure of lactic acid, we again put the Fisher's projection in a vertical line, and the vertical line was preferably satisfied by the carbon, preferably. That too, COOH was occupying the top position, because by convention, the most oxidized functional group to be written at the top in the Fisher's projection, meaning on a vertical line. So A and D, which you have written, are generally or preferably should be carbon containing. A and D. I'm saying preferably because sometimes you might not have an option. Preferably carbon containing, in whichever is highly oxidized. Like if you have got acid, A should be acidic group. If it is aldehyde, it should be aldehyde group. Okay. So now here, let's assume A and D are carbon containing. So A and D. So this is your D and this is your A. So see, we want this position because A and D is a set of 2. So here set of 2 is this and this. So I want A and D to be brought here. A is, where is A? Okay, A is here. So you want this A to be brought here. Everyone here. If you want to bring this A here, so tell me how much degree rotation is required. Well, this is carbon-carbon single bond, so rotation is possible. So here, in order to bring this A here, everyone's here. This A from here, I want to bring it here. This dotted line indicates where you want this A. You want A here, no? So how much rotation is this? This is 60 degree rotation. So let's call this is front carbon and this is rear carbon. I'm calling this is front carbon because I'm assuming an observer is observing the molecule from here. So let's say this is observer's eye. That is an observer eye who is observing molecule from here. So this carbon he will encounter first. So this is front and that is rear. So at the rear carbon, you want A to be rotated clockwise 60 degree. So if A rotated clockwise 60, even F will go 60 degree up, meaning it will go somewhere here. So this will be your, which group? This will be your, F will go there. So that is your F. Okay, let's, guys, I'm just interchanging the position. I'm making this is B and this is A. I'm making this is B and this is F. Okay. So if you bring A here, B will go up here. So this is going to be your B. So if clockwise I'm rotating, even F will be rotated 60 degree clockwise. So F 60 degree clockwise will come here. So that's your F. Okay. So I'm trying to achieve what I want so that conversion of source into Fisher will become easier. So this was the rear carbon. This is the front carbon. At front carbon you wanted what? Set 2 of 4. So A and D is considered as set of 2. So we want D here. So D is already here, meaning the C and E will remain as it is. Okay. Now see, conversion of this into Fisher becomes easier. How? This is front carbon. This is rear carbon. When you convert Sohor's into Fisher, this is only possible when you have a group in a set of 2, 4. So assume imaginary plane. In one plane there were 4 groups. In other plane there were 2. So that's absolutely fine. If you write 2 up and 4 down, that is fine. But in one plane there has to be 2. In other plane there has to be 4. Now if you convert them into Fisher at the front carbon, remember always at the front carbon write down the group which is to the right, left, and then the remaining one. So at front right is E. At front right is E. At left there is C. So the remaining is D, which you see here. At the rear carbon, what is to the right? F. So at the rear to the right we have got F. To the left B. To the left we have got B. Remaining is A. So this is your remaining A. So we will always try to convert a given molecule into such a Sohor's where its conversion into Fishers will be easier. Such a Sohor's meaning you need a group in a set of 2, 4. Then only conversion into Fishers become easier. Now let me straight away apply this to the question. These are the molecule given. They are asking us to find a relation of M with rest all. JEE Advanced 2012 question. How do we do that? Well, guys, we'll always try to convert the molecule into features. How do we do it? Look. Well, let's assume this is front carbon and this is rear carbon. We want this to be brought in a set of 2 and 4. In fact, the way they have given it is already in a set of 2 and 4. I'll still do it one more time. Look. Okay. So we have a front carbon here and the rear carbon here. So if you consider the imaginary plane like this, 4 are above the plane, 2 are below the plane. So we have got our required 2, 4 set. 2, 4. But at 2 meaning in the feature are this 2. 2 meaning in the feature are this 2. So they should be preferably carbon containing. So that's why this is carbon containing. So this I'll be taking methyl. Everyone here? This is methyl. Now at the rear carbon we don't have methyl, so let's assume that to be chlorine. So already methyl and chlorine are pointing downward, meaning this is your OH and this is your H. The way they have represented is little different, but this is the H, okay, which is ideally supposed to be like this. At the rear to the chlorine, what is to the right? H. What is to the left? OH. Next conversion, this one. Now look here. Now at the front carbon they have put chlorine. That is absolutely fine. At the front we have got chlorine. Then to the right we have got OH. To the left we have got H. At the rear we have got methyl pointing downward. Okay. To the right we have got H. To the left we have got OH. Okay. O. In O, well, in a set of 2 and 4, now there is no set of 2 and 4. Above the plane there are 3, below the plane there are 3. So we'll have to rotate it. So let's say the rear carbon, if I'm rotating clockwise, 120 degree. 120 degree meaning where you see chlorine, it will take a place of OH. Not 120, I think we'll have to rotate 180 because chlorine is pointing upward. So rotate it 180. So chlorine will come down. H will be rotated 180. So there will be H. OH will go 180. So that's your OH. And this is as it is. CH3. Because this is the place where we always wanted methyl. To the right we have got H. To the left we have got OH. See guys, the whole idea is to bring the group in a set of 2, 4 so that representation of this molecule into features become easier. So set of 2 meaning 2 are generally carbon containing. So at the front carbon we have got methyl, but at the rear we don't have any carbon containing group. So I assume it to be chlorine. So every time I'm trying to do the same thing. I did that here as well. Okay. Well, now this is the Newman projection. How do we convert that Newman into Sohars and then eventually into features? Well, such Sohars, such Newman, to convert that into feature, the requirement is that, look, I'm putting that here. This should be represented this way. This is the front carbon. And this is the rear carbon. So if you consider this as the imaginary plane, you can see above the plane there are 4, below the plane there are 2 groups, right? So the 2 are always going to be carbon containing. So what do we want? At the front carbon, we always want CH3. So we want CH3 here. To bring this CH3 down here, you have to rotate 180. So the front carbon to be rotated 180. So methyl will come here. So OH will go 180 to the right. This is OH. H will go 180 to the left. That is H. At the rear carbon, you already have got chlorine. So at rear, you don't have to do anything. So you see chlorine is right here. OH is over here. And at the rear carbon, H is to the left already. So converting this into Sawhorse, this is your front carbon. At front, pointing downward is CH3. To the right is OH, to the left H. At the rear carbon, pointing downward is chlorine, right? Because you rotated it 180 degree. To the right, we have got OH. To the left, we have got H. So that's a conversion of Newman into Sawhorse. So that's your P. And now let's talk about Q. Well, in Q, everyone, what we want methyl here. We want chlorine here so that we can compare them all, correct? So to do that, see methyl at the front carbon, this is front and this is rear. So front has to be rotated 180 degree. So methyl will come down. So OH will also go 180 degree opposite. So OH, from here it will go up here, OH. So at the front carbon, H will also be rotated 180. So here is your H. At the rear carbon, chlorine is downward, that's fine. Hydrogen is to the right and OH is to the left. Alright everyone. So that's how we got conversion of M, N, O, P and Q into their corresponding Sawhorse. And now I'm going to compare them by putting them into Fishers. So this will be converted to Fisher this way. Everyone here? Guys, hold on. Just keeping arrangement ready. Second, that is third. Fourth. And this is fifth. Okay, now simply the one which is down here would be our front and this is going to be rear. Okay, always that's front and this is rear everywhere. Now at the front carbon, what I've told you, whenever you represent molecule into its Fisher, always make sure you put the group which is to the right, then to the left and the remaining one, whether up or down, that's not a problem. So at the front, what is to the right? H. So I put H. What is to the left? OH. Remaining is methyl. Put it that way. At the rear carbon, what is to the right? H. What is to the left? OH. And the remaining is chlorine. Whether down or up, you have to put it whatever is left. So chlorine is left up. So although chlorine was downward, I'm putting chlorine here. That's front and rear. Now this is little different because in all other cases at the rear carbon you have got chlorine. See, at the rear you have got chlorine, at rear you have got chlorine. Only this is the molecule where at front we have got chlorine, but we can rotate it 180 degree within a same plane. Meaning at the front carbon, to the right I have got OH. To the left I have got H. Remainder is chlorine. At the rear carbon, to the right you have got H. To the left OH. Remainder is CH3. Okay. Now guys, to be able to compare this, just imagine if I rotate the whole molecule 180 degree within the same plane. So we can compare it in a way we are doing it, meaning then this can be simply represented like this. Whole 180 degree being upside down. So chlorine will go up here. The H which is to the left will go to the right. The OH will come to the left. And methyl will come down. This OH will come to the right. and H will come here. Okay, everyone, meaning basically you're rotating the whole 180 degree within a same plane. So OH and H will come to the right, H and OH will come to the left. Perfect. So that's your N. Now that was your O. At the front carbon to the right I have got H. Look, at the front I have got H to the right, OH to the left. And the remainder is methyl. At the right carbon to the right I have got H, to the left I have got OH, and the remainder is chlorine. Right, everyone? P, structure P. At the front to the right OH, at the front to the right we have got OH, to the left we have got H, remainder is methyl. At the rear to the right we have got OH, to the left H, remaining is chlorine. Correct, everyone? And finally the structure number Q. At the front we have got OH to the right, H to the left, remaining is methyl. At the rear we have got H to the right, OH to the left, remaining is chlorine. Well, let me now designate them once again. This is P, M. This is N. This is O. That is P. And that is Q. Now we just have to compare the relation. Well, few minutes back in the features we saw how to find out enantiomers, how to find out diastereomer, how to find out meso. Enantiomers were optically active isomer of the same compound which were mirror images. Okay, but optically active, so there should not be plane of symmetry. Diastereomer are stereoisomeric pair which is non-mirror images. And meso meaning two chiral carbon but will have a mirror plane of symmetry. Now guys, once you have converted them into corresponding features, refer to the question statement. M and N are non-mirror images stereoisomer, meaning they are talking about these two being diastereomers. Diastereomers. Well, let's check that. Are they diastereomers, M and N? M and N are diastereomer. Well, compare these two. This is chiral, even this is chiral carbon, no plane of symmetry. This is chiral, no plane of symmetry, both optically active. And are they mirror images? Look, against H we have got OH. So these two are definitely not the mirror images. So the pair of stereoisomer which are not a mirror images are what? Diastereomers. So M and N are certainly diastereomers. So this statement is absolutely correct. B says M and O are identical. M and O are identical. Are they? M and O are identical. Well, you can say absolutely. Look, chlorine, OH and H. Chlorine, OH and H. Down here, OH, H and methyl. OH, H and methyl. So M and O are identical. So M and O are identical. M and P are enantiomer. Enantiomeric meaning mirror images. Which two they are talking about? M and P. M and P. M and P. Yes, they are mirror images. Can you see? To the right I have got H, here I have got H to the left. Again, at front carbon H to the right, at front H to the left. Imagine if you put them together against each other. M and P will be mirror images of each other. So yes, M and P are mirror images, meaning they are enantiomeric pair. And finally, M and Q are identical. M with Q, are those identical? No, they are not. Look, M you have got OH to the right, OH to the left, H to the right, which is correct here. But at the front carbon, OH is to the left. Here at the front carbon, H to the left. So M and Q are not identical. So this statement is not correct. So in this multiple options correct, the correct options for us are M, A, B and C, all three. Guys, the whole idea of solving this question was to be able to put this molecule in the form of the Fischer's projection converting sawhorse into fisher, you only have to remember, in whichever way sawhorse is given to you, you always have to bring sawhorse in this form. Which form? Either this form or in this form. Basically, the idea is, if I consider an imaginary plane like this, if 4 are in one plane, 2 should be in other plane. So whether you put 2 downward or in this way, we have put 2 upward. So we want the group to be always in the set of 2 comma 4, and the 2 are preferably going to be carbon containing. So we can easily convert them into the fissures. Once you are able to put them in the fissures projection, then you can simply relate it the way we have done it. So guys, that was all about the optical isomers and finding out the relation between them. Let me just add one more point for you all. Always remember, when the two isomers of enantiomers of each other, when two isomers are enantiomeric pair of each other, the RS designation at every chiral carbon has to be always opposite. Like M and P are enantiomers. Where is that? M and P are enantiomers. So whatever designation you will have here, let's say if it is R, then this has to be S. If this is S, then this will always be R. In a pair of enantiomer, every chiral will always have opposite designation. And in case of diastereomer, like here, we realize that M and N are diastereomers. M and N are diastereomer. So if one chiral carbon has same designation, let's say this is R, so even this will be R, and at least one has to be different. So at least one chiral will have identical designation of RS, and at least one have opposite designation. So if you have to compare two enantiomeric pair or diastereomeric pair, if by comparing the structure, if you are not able to do it, simply find out RS designation. At every chiral carbon, if you see the designation as reverse, let's say in structure A, it was 2R, 3S, and in B it became 2S and 3R, then those two will always be enantiomer. Whereas if at least one has identical RS designation and at least one has opposite, those will always be the enantiomers, diastereomeric pair of each other. So guys, that was all about the optical isomers. And now we're going to proceed with reaction mechanism, but we'll be taking short break of 15 minutes once again, and I'll see you there again in 15 minutes. Guys, can you hear me, everyone? Everyone, can you hear me? Okay. Guys, more than the speed, it is very important that you are able to understand whatever I'm making you understand. So it's not just about the speed. You guys have to make sure, you have to ensure that you're understanding. So if I would have gone really too fast with the questions of JEE Advanced, probably it would have been cause some difficulty to you. So we are just ensuring that you guys are understanding every small information that we are conveying. Great guys, so we'll be taking short break of 15 minutes and we'll be right back with the next part of reaction mechanism and further reaction part. I'll see you there. Yes, Rakshita, beta will try to cover up all the concepts which you need for even NEET, okay? So whatever we are learning, those are important ones for even NEET. Don't worry, so just stay focused. I'll see you there in another 15 minutes. Hello, hello. Hello everyone, can you hear me? Hey guys, can you hear me? Hello, hello, hello. Am I audible everyone? Okay, Harshvardhani. Okay, okay, Nilesh. Okay, I got it. Yes, Jiva, I'll try to. Just a moment, guys. Hi, Varman. Hey guys, welcome back. Hope you enjoyed your small break. Excellent. Okay, Avantika. RR, hi, hello. Yes, Varun, thank you so much. Lakshmana Kumar, beta, ignore them, that's fine. Okay, guys, chalo, let's get started. Well, so far we talked about GOC, we talked about isomerism, and most of the important concepts have been covered. So we are going to start with the third one, reaction mechanism. Well, you must have seen that often the questions of alkyl halide have been clubbed with the reaction mechanism. So doing reaction mechanism is really very important. So we are covering this topic here. Well, guys, commonly you see the questions have been asked where there will be comparison between SN2 and SN1, similarly between E1 and E2, and there might be a comparison of substitution versus elimination as well. Hence, we will first learn that how to identify whether given reaction is undergoing via SN2, SN1 or E1 or E2 mechanism. So for which some data is required for us to be known first. So when you talk about SN2 and SN1, some of the key features that you all will have to always remember, like when you talk about SN2, always remember SN2 is a concerted mechanism. Now what does concerted means? When bond breaking and bond making takes place simultaneously. When nucleophile attacks at the deficient carbon and simultaneously leaving group leaves, you call it as concerted step. So SN2 is one step mechanism which is called concerted, whereas SN1 is a two steps reaction. SN1 is a two steps reaction where first step is formation of carbocation. Carbocation formation. So these are the two important key features of SN2 and SN1. Whenever there is SN2, it will always be a concerted step, meaning bond making and bond breaking will take place simultaneously. And whenever it is undergoing SN1 reaction mechanism, there will always be a formation of carbocation. Now let's talk about several factors which favors SN2 mechanism. So when you talk about substrate, SN2 is the only mechanism which takes place at a lesser sterically hindered carbon atom. Hence, methyl halide will always be the most reactive substrate towards SN2, followed by primary alkyl halide, followed by secondary alkyl halide, and tertiary alkyl halide won't give SN2 reaction at all. So sometime by looking at the substrate, it becomes easier for us to decide whether reaction is going via SN2 or SN1. Next, when you talk about nucleophile, refer to the key feature. Key feature of SN2 is that it is concerted step, meaning simultaneous attack of a nucleophile at the deficient carbon with the simultaneous departure of a leaving group. For such step to take place, the nucleophile has to be always a stronger nucleophile. So stronger nucleophile meaning anionic. So stronger nucleophile favors strong nucleophile, meaning anionic nucleophiles, favors SN2. So favors SN2 is what we know, so I'm not writing that. So stronger nucleophile meaning anionic. So if you see a reaction is given with OH minus ion or RCOO minus ion or methoxide ion, those are the kind of nucleophile which being anionic will always favor SN2 reaction. Leaving group, well, leaving group universally has to be always a good leaving group. So whether it is SN2, SN1, E1 or E2, it has to be always a good leaving group. So when you talk about order of leaving group ability, always remember that iodide is the best leaving group among halogen, followed by bromide, followed by chloride, and then the poor leaving group among halogen is F. So this has to be the preferred order of leaving group ability. Solvent, well guys, we said we want nucleophile to be stronger. We want nucleophile to be stronger, meaning anionic. Imagine if you want anionic nucleophile to carry out this SN2 reaction, and if you're using a polar protic solvent, then the protic part of that solvent will always form hydrogen bond with that anionic nucleophile. Such nucleophile will then be captured or will be then bonded to a polar protic solvent. So the nucleophilicity, the movement of nucleophile in the solution will get restricted. So the nucleophile will no more remain stronger nucleophile. Hence, we always ensure that the solvent which is used is not going to capture the nucleophile. So we shouldn't use polar protic. Hence, polar aprotic solvent favors SN2 reaction mechanism, polar aprotic. So these are the factors which favors SN2 reaction mechanism to takes place. Now if we compare the same thing with SN1, well guys, another important feature that we always should keep in mind is the rate expression. For SN2, rate expression is R is equal to K into molar concentration of substrate into molar concentration of a nucleophile. Okay, now when you talk about SN1, we say the rate of reaction is equal to, meaning proportional to molar concentration of only substrate. This indicates there is no role of solvent here. So irrespective whether you increase or decrease the concentration of a nucleophile, it is not going to affect the rate of SN1. Anyways, let's talk about the substrate. Well, SN1 reaction mechanism's key feature is formation of carbocations. So guys, logically, what kind of alkyl halide will form relatively stable carbocation? If you compare tertiary, secondary, primary and methyl, keeping the fact in mind about the order of stabilities of carbocation, we know that the tertiary alkyl halides will form most stable carbocation, and hence the rate of reaction towards SN1 will be fastest in case of tertiary alkyl halide, followed by secondary alkyl halide, and the least will be for primary. We should not even consider methyl because the carbocation corresponding to methyl group is going to be highly unstable. So that is the decreasing order of reactivity of alkyl halide. Next is nucleophile. Well, the rate expression does not even include nucleophile. So weaker nucleophiles. Weak nucleophile favors SN1, meaning generally solvents. Generally solvent itself acts like a nucleophile. Look, when you talk about SN2, you need stronger nucleophile, meaning you need anionic nucleophile. But in case of SN1, weaker nucleophile, meaning solvent itself. So like if I talk about water, water is a solvent itself. So water is a neutral species, it is not anionic, so it is not strong one. So the neutral molecules such as water being weaker nucleophile favors SN1 reaction mechanism. Now because we use solvent as a nucleophile here, SN1 reaction mechanism sometimes also referred as solvolysis. Leaving group, well I've talked about leaving group, universally it has to be always good leaving group. Finally, solvent. Well, guys, have a look at the key feature. Key feature is to convert alkyl halide into its corresponding carbocation. In order to convert alkyl halide into its corresponding carbocation, we need a heterolytic fission between the carbon and the leaving group covalent bond. That heterolytic fission of a carbon and halogen leaving group, that is halogen covalent bond, can be enhanced by using a polar protic solvent. Hence, if we take a polar protic solvent, it helps the dissociation of a carbon and leaving group bond, and not only that, even after dissociation, the carbocation which is formed will be stabilized by polar protic solvent by ion dipole interaction, and leaving group, generally halide ions, can be stabilized by hydrogen bonding. So for SN2 we need polar aprotic solvent, but SN1 reaction will always be favored by polar protic solvent. So what do we need here is polar protic solvent. Alright, so that was all about comparison of SN2 versus SN1. Similarly, we'll talk about E2 versus E1. So just like we said, SN2 was concerted, even E2 is concerted. The only difference lies between SN2 and E2. In SN2 we had a nucleophile, so that's why it was simultaneous attack of a nucleophile and simultaneous departure of a leaving group. In E2 we don't have a nucleophile, we have got a base. So the role of base is to not to attack at the deficient carbon but to abstract the beta hydrogen. So when abstraction of a beta hydrogen and departure of a leaving group takes place simultaneously, we call it as bimolecular elimination, that is concerted step. Now the rate expression here is rate is equal to constant K into molar concentration of substrate as well as base. So base also appears in the rate expression of E2. Whereas when you talk about E1, the key feature here is just like SN1, that is formation of carbocation. So guys, like we said, SN2 is a one-step reaction, SN1 is a two-step reaction. Similarly, E2 is a one-step reaction, E1 is a two-steps reaction, where first step is formation of carbocation. So the rate expression here is rate is equal to constant K into molar concentration of substrate only. There is no solvent, there is no base which is appearing in the rate expression, so it is independent of concentration of a base. Well, another features here. When you talk about E2, the order of reactivity of substrate, tertiary is most reactive, followed by secondary, followed by primary, and methyl does not even come into picture because methyl does not contain beta hydrogen at all. So no question of beta elimination, and E2 is a type of beta elimination. So if you see the difference here, only SN2 is the one where least sterically hindered substrate is most reactive. Rest in all cases, you will see more sterically hindered substrate is going to be the most reactive one. So when it comes to E2, in case of E2, tertiary alkyl halide will be most reactive because of two reasons. Number one, more substituted alkyl halide will have more number of beta H which can be abstracted by the stronger base. And once the stronger base abstract the beta hydrogen atom, the corresponding alkene form is more substituted alkene, meaning more stable alkene thermodynamically, which we get only in case of the tertiary alkyl halide as compared to secondary and primary. That's why this is the order. Base, like SN2 you need stronger nucleophile, here we need strong bases. But this is something important, I want everyone to pay attention. When it comes to E2, I want you guys to remember 5 important bases which are more commonly used when they have to give question related to E2. Those stronger bases are, well, to remember, start with the term alcohol. So first one, remember alcoholic KOH. From the alcohol, remember conjugate base of ethyl alcohol. So ethyl alcohol is C2H5OH, so its conjugate base is ethoxide. Sodium or potassium, any metal, and you can put it here. Just like ethanol, you can remember methanol. So methoxide is also another strong base. Other than alcoholic KOH, then ethanol, methanol, remember tertiary butanol. that is tertiary butyl alcohol. So CH3 thrice CO minus can be balanced by any cation, sodium or potassium, and then finally sodamide, NaNH2, or potassium amide is also fine, by the way. So guys, these are the 5 bases. Alcoholic KOH. How will you remember? Start from term alcohol. Alcoholic KOH, and from alcohol, ethanol's conjugate base, methanol's conjugate base, tertiary butyl alcohol's conjugate base, and sodamide. If you see that these 5 bases are given, then in most of the cases, the reaction is going to be E2. Only there could be a possibility of SN2 when, imagine if alkyl halide is methyl halide, then methyl halide does not give you E2 at all. So in that case, this anionic species, instead of behaving like base, will behave like a nucleophile, and you're going to get SN2 type of reaction mechanism. But otherwise, this basis will always bring out E2. Leaving group, no surprises. This has to be always a good leaving group. Good leaving group. And solvent, you want stronger bases to remain stronger base to carry out concerted step. So we have to ensure that strong bases are not getting bonded to any solvent, meaning you don't need a polar protic solvent, otherwise they'll bind those strong nucleophiles. So the solvent has to be what? Polar aprotic. So I will say polar aprotic solvents will favor E2 reaction mechanism. And now coming to even, I want you guys to refer SN1 once again, because everything is going to remain same. Whatever condition you see for SN1, same remains for even. Order of reactivity, tertiary to primary. Nucleophile, now we are going to have a base. So just like weaker nucleophile will have a weaker base, generally solvent. Leaving group, as always, has to be a good leaving group. Solvent has to be polar protic again. The only difference you are going to see is about temperature. So first, substrate, because the key feature is formation of carbocation, tertiary alkyl halides carbocation is most stable. Yes, that is the most reactive ones. Base, the base will always be a weaker base. Weak base, generally solvent itself, like water, methanol, any of that sort. Generally solvent. Guys, trust me, if you do this, at least you'll be able to solve many questions from the reaction mechanism part, okay? So this is the basic information you guys need to know. Leaving group, like I said, good leaving group. Solvent, well, you want carbocation to be formed. Carbocation formation will take place when the bond between carbon of alkyl group and the halide group will be broken. Breaking of that sigma bond between carbon and leaving group can be enhanced by taking polar protic solvents, because the role of polar protic solvent is not to dissociate the bond heterolytically, but also once those carbocation and the leaving group are formed in the form of anion, those to be stabilized. Hence I'll say polar protic solvent. Polar protic solvent will favor even mechanism. Now see, if you see all these 4 factors, they are exactly like even, exactly like SN1. So question arises, if I have been given tertiary alkyl halide, if I have been given water as a solvent with a good leaving group such as iodine, then how do I find out whether the reaction mechanism path is going to be SN1 or even? So guys, the only factor that distinguishes between SN1 and E1 is the temperature. Whatever condition I said just now, tertiary alkyl halide, solvent as a water, iodine as a leaving group, and on arrow if you see the heat is mentioned, symbolically a triangle is mentioned, then that will indicate it is even and not SN1. So higher temperature will always favor E1 mechanism over SN1. Keeping these all facts in mind, guys, let's have a look at 2 questions here. So that is JEE main. You can see September 2020 shift 1. Question says the mechanism of SN1 reaction is given as follows. Well, So like we said, in SN1 what happens? Alkyl halide will dissociate the carbon halogen bond in presence of polar protic solvent to give you R plus and X minus, that is ion pair. So step number 1 is achieved, formation of carbocation. Once carbocation is formed, then the nucleophile attack at the deficient carbon to result in the formation of the corresponding product. Right, everyone? Now, okay. So once you get this, now the question says, so general characteristics based on the given mechanism are as follows. You have to find out the correct one, right? Hold on, everyone. Okay. Which observations are correct among this? All right, guys. So the reaction is favored by a weak nucleophile. Firstly, they are mentioning about SN1. If it is SN1, is it favored by weak nucleophile? Yes, of course. Solvent itself. So statement A is correct. It is favored by weak nucleophile. B, R plus would be easily formed if the substituents are bulky. What was the key feature of SN1? SN1 says the formation of carbocation is the key feature. So for that to happen, the alkyl halide has to be sterically hindered like tertiary. Sterically hindered meaning bulky. So yes, R plus would be formed easily if the substituents meaning substrates are bulky. C, the reaction is accompanied by racemization. Well, let me tell you. See, if you're getting formation of carbocation, let's assume a case like this. If a carbocation is formed with the three different groups attached here, let's say phenyl, methyl and ethyl, just for the understanding, and carbocation formation because they're talking about SN1. And now when nucleophile is going to attack, let's say water is the nucleophile which is going to attack here, followed by deprotonation. Now I want you all to understand, first of all, the carbocation indicate that this is in sp2 hybridized state, which means the geometry of this molecule is planar, isn't it, everyone? If this is a planar carbocation, then the attack of water molecule can take place either from the front side or from the back side. And the corresponding product obtained will be a tetrahedral carbon. See, now we have got three bonds. The new bond between oxygen and carbon will make this carbon tetravalent. So the four groups attached to this carbon will be phenyl, methyl, ethyl and OH. Since all the four groups attached to this carbon are going to be different, this is going to be a chiral carbon. And today in the first half of this one shot complete organic chemistry, we discuss in isomerism. If molecule contains one chiral carbon, it will always be optically active. So I am going to get optically active compound either by the attack of OH from the front side or from the back side. So those two optically active compounds will be what? Enantiomers of each other. So if you're getting two enantiomers of the same compound, then that mixture is what you refer it as the racemization, meaning this reaction is certainly accompanied by the racemization. So this is the correct statement as well. Finally, the reaction is favored by the non-polar solvent. Absolutely incorrect. Why? Because for carbocation to be formed, we need a polar protic solvent with a high dielectric constant that helps the dissociation of a carbon leaving group bond. And even after departure, the carbocations and the leaving groups are stabilized by either ion dipole interaction or hydrogen bonding, respectively, for those two. So statement D is incorrect. So A, B, C are correct ones. So among these options, option C fits well in here. A, B, C, all three are correct. Guys, just like this, let's have a look at one more question. 2019 JEE Main 10th April shift 1 question. So yet another PYQ. They have given some substrate and some solvent. And you have to identify that which mechanism will it follow, because based on mechanism you can write down the corresponding product. Okay. Now how do we zero down among the mechanism? Well, tell me first, what are the probable mechanism we can think of? We can think of SN1, SN2, E1 and E2, right? Okay, let us first talk about the substrate. From the substrate, we find out what mechanism will it follow looking at the degree of alkyl halide. So the carbon to which leaving group attached is secondary. So the existing alkyl halide is secondary, but not to forget, adjacent to secondary carbon, we have got tertiary carbon as well. Meaning, I'm keeping one thought parallelly in my mind. In case if the carbocation is formed at the secondary carbon, then this hydride can shift at the adjacent carbon, generating this tertiary as tertiary carbocation, which is more stable carbocation. Meaning there is going to be possibility of formation of carbocation. Just a parallel thought. Otherwise, if I look at the reagent given is methanol. So it is a neutral molecule. It is not anion. If it is not anion, it is neither strong nucleophile nor a strong base. So SN2 and E2 are ruled out. Because for SN2 you need strong nucleophile, meaning anionic nucleophile. For E2 you need strong bases. Out of those 5. Which 5? Alcoholic KOH, ethoxide, methoxide, third butoxide and sodamide. This is none of that. Which means now I can certainly say E2 is not possible, SN2 is not possible. Only option left is SN1 and E1. Now guys, in case of SN1 and E1, when you compare, the simple trick I have told you, if you see there is a heat given, a temperature, it is even, otherwise SN1. I don't see any temperature, so E1 ruled out. So mechanism is SN1. So carry out SN1. What do you do in SN1? First, carbon leaving group bond breaks and you get carbocation. So if this bond is broken, we will be getting CH3 carbon carrying methyl, and this is the tertiary carbon we were talking about. So we have got H, and now CH plus and CH3. See student, this is what I was talking about. The existing carbocation now is secondary. But when existing carbocation is lesser degree and adjacent carbon is of higher degree, which has ability to rearrange and form more stable carbocation, then rearrangement will always take place. So if existing carbocation is secondary and adjacent is tertiary, remember there will always be a hydride shift. So H minus shifted from here to here. So under what circumstances are we supposed to do shift? Remember that if existing carbocation is lower degree, adjacent carbon is higher degree than itself. Meaning adjacent to secondary carbocation there is 3 degree carbon, or adjacent to secondary carbon there is quaternary carbon. So because adjacent carbon are of higher degree, there will always be a shift or the rearrangement taking place. If adjacent carbon is 3 degree, there will be hydride shift. Had it been quaternary, the methyl shift would have taken place. Hydride shifted. Well, as a result of hydride shift, we got CH3, a carbon, CH3. Now see, this was CH, one more H will come here to make it CH2. And then we have got CH3. Because of that hydride shift, the tertiary carbon became cationic. So now we have got 3 degree carbocation. Once you get 3 degree carbocation, now your solvent methanol is all set to attack at the deficient carbon from both the side, front and back. That's how we are going to get racemization. So let's say methanol is attacking OHCH3. Electron rich oxygen being nucleophilic, all set to attack. So let's say methanol's oxygen attacked here, followed by deprotonation. So effectively what is going to get added? Methoxy, CH3O, and the nucleophilic atom is O. So in your product, at this carbon you will be having OCH3 attached. So the product, I'll write it here, CH3, CCH3, carrying ethyl group to the right here. Guys, hold on. And who attacked here? Effectively OCH3, meaning methoxy. So we will be getting OCH3 here. Guys, which option do you see fitting well in here? Methoxy at, meaning okay, so there is your option, option C. Right everyone, that's how, looking at the conditions given, I first figured out which mechanism will it takes place. Once you decide which mechanism it is going to follow, then keeping the mechanism in mind, carry out the reaction. if SN1 or even, just ensure that if the formed carbocation is not the most stable one and has a scope of undergoing rearrangement to form stable carbocation, do that and get the corresponding product. Alright guys, are we all understanding here? Yes, perfect. Nilesh, Umay, Wali, Rajiv Kumar. Alright. Devesh, perfect, perfect, perfect. Lovely guys. So that was all about SN1 and SN2, and that's how you can compare substitution reaction versus elimination reactions. Taking discussion ahead towards hydrocarbon. Well, entering into hydrocarbon will be taking care of few important reaction. Of course, the time is not allowing us to do everything, but like I said in the beginning, we will be covering some important chapters, and in chapters also we'll be taking care of the most important reaction. So here is the first one. Well, this is nothing but preparation of alkene from unsaturated hydrocarbons. So everyone, when you talk about unsaturated hydrocarbon, of course those are alkenes and alkynes. Now we are learning method of preparation of alkenes. So the unsaturated hydrocarbon has to be other than alkene. So what is left is alkyne. So from alkyne we can convert that into alkene. However, let me just brief you something. See, in general, when we study catalytic hydrogenation, which we also call it as Sabatier's endurance reaction, what we do, we take an unsaturated hydrocarbon like alkene or alkyne. We pass hydrogen gas in presence of metal catalysts such as nickel, platinum or palladium. Those metal catalysts, we refer them as active metal catalysts. Active metal catalysts are the one which provide the surface area for a large concentration of hydrogen gas to get absorbed on its metal surface. And then those excess amount of H2 gets added across carbon-carbon double or triple bond, and straight away we get our product as alkane. Which means controlling the reaction from unsaturated hydrocarbon in between. For example, if I've got alkyne, then converting alkyne into alkene will always be going to be difficult, because the concentration of hydrogen gas getting absorbed on an active metal catalyst is going to be very high. Hence, controlling reaction in between is always a challenging thing. However, that can be achieved by using a special type of catalyst called as Lindlar's catalyst. Guys, let me just brief you first what is Lindlar's catalyst, because you may have some, you can say a question on this, not related to directly reaction but also about reasoning of this reagent. Okay, so Lindlar's catalyst is nothing but palladium metal coated on calcium carbonate or barium sulfate, sometime in presence of small amount of lead or lead acetate, with quinoline or sulfur containing substances, which is called as the poisoning substances. Now what does exactly this poisoning substances means is, look, when palladium is coated on calcium carbonate or barium sulfate, it basically decreases the surface area of palladium. Also, addition of poisoning substances such as sulfur or sulfur containing compound like quinoline does not allow high concentration of hydrogen gas to get absorbed on a metal. If the concentration of hydrogen gas getting absorbed on palladium metal decreases, then the addition of H2 from the same side, that is from the syn side, become lesser and lesser. So let's say only one equivalent of H2 have been added here. So what will happen? One of the pi bond would be broken, two new sigma bond will be formed between carbon and hydrogen, and as a result of which we will be getting formation of products such as RC, double bond Cr, and both the H's which are newly added will be added from the same side. So both will appear on the same side of carbon-carbon double bond, resulting in what stereochemistry of product? Cis. So the product obtained will always be a cis alkene. So the role of calcium carbonate or sulfur containing substances is basically to poison the metal catalyst and not let it be active as it is otherwise in case of catalytic hydrogenation. If metal catalyst is not that active, then the concentration of hydrogen gas getting adsorbed on that will decrease. So the addition of hydrogen won't be exhaustive as in case of hydrogenation. So we can control the conversion of alkyne into alkene. But because the addition takes place from only one side, we refer it as syn addition. Hence, the alkene obtained will always be cis alkene. For example, if we have got 2-butane, if we add hydrogen gas, then that 2 H's will be added from the same side of carbon-carbon triple bond, resulting in the formation of product, which is CH3H double bond C CH3 and H. So guys, this is nothing but cis 2-butene. We studied how to name geometrical isomers. So this is nothing but cis 2-butene. So unsaturated hydrocarbon like alkyne can be controlled to alkene with a specific stereochemistry of cis alkene by a special reagent that is called as Lindlar's catalyst. Lindlar's catalyst is palladium metal on calcium carbonate or barium sulfate in presence of some amount of lead or lead acetate with sulfur containing compounds such as quinoline. Okay, so this is your basically a poisoning substance. Just like that, alkyne can also be converted to alkene, but into a trans isomeric form with the help of a reagent called as Birch reducing agent, and the reduction is referred as Birch reduction. So what Birch reduction does is, if I just write down the conversion, I would say non-terminal alkyne when treated with sodium metal or lithium metal in liquid ammonia will result in the formation of an alkene, but this time the 2 H's which you see have been added would be on the opposite side of carbon-carbon double bond. This tells us about the stereochemistry of product, which is going to be trans alkene. So conversion of alkyne into cis alkene can be achieved by use of Lindlar's catalyst, and converting alkyne into trans alkene can be achieved by Birch reduction. Now what happens in Birch reduction? Let us see that. Everyone here? So let's say we have got any of the metal. I'm taking sodium metal. Metal, because of their low ionization enthalpy, they can easily release electron to a deficient site. So let's say we have got RC triple bond Cr. Okay, so let's say Na donated its electron to the carbon atom, which polarized the pi bond towards another carbon, as a result of which we now got RC carrying odd electron, double bond C. Now you see the entire pi bond localized over carbon, so this became anionic, and then we have got another R. Fine. This anionic carbon indicates that it is a conjugate base of alkene. Guys, what is alkene? Alkene is a doubly bonded carbon, and let's say it is unsubstituted, so there is one H present. So if that H is lost from an alkene, you will get anionic character on the carbon atom. So this indicates it's a conjugate base of alkene. Now alkene being very weak acids, its conjugate base is going to be very strong. Because this is a very strong conjugate base, it will always attack at anything that is protic. Now since we have got liquid ammonia, this hydrogen atom connected to nitrogen is certainly protic. Anything we refer it as protic which is connected to electronegative atoms. So this anionic carbon will attack at H plus, sigma bond will break towards NH2, little correction here, that's NH2. Yes. So we got RC odd electron, double bond C, H and R. Okay. Now the second equivalent of sodium metal will donate its electron to the existing radical here and will convert even this carbon into anion. So we will be getting RC double bond C carrying H bonded to R, and this is the anionic carbon. Now this anionic carbon is all set to attack at anything that is protic. So let's say we have got H, NH2. So the anionic carbon attacked at the proton, this bond broke over N and NH2 minus. So sodamide will be lost as a byproduct. Guys, eventually see what we got. We have got R, CH, double bond CH and R. So the alkene octane is such where we have got two identical atoms are on the opposite side of carbon-carbon double bond. We refer this as what? Transalkene. So that's how alkynes can be converted to cis-alkene using Lindlar's catalyst, and the alkynes can be converted to transalkene using Birch reduction. So guys, can we just attempt this question based on what we have learned? I think you're going to solve this like less than even 5 seconds. The transalkene are formed by the reduction of alkynes with, well, the moment I read this, trans alkenes from alkynes, so it has to be what? Birch reduction. Birch reduction is sodium metal in liquid ammonia. That is our answer, option C. All right, everyone. Okay. Everyone, are we all there? Perfect. Rakshita, Devesh. Yes, Karthik, that is absolutely sufficient. Okay, perfect, perfect. Everyone? Next reaction is halogenation. I would say this is another important reaction. First, I'll explain it to you conceptually, and then I'll tell you simple trick. How can you apply this trick and get the answers quickly? Okay, everyone pay attention here. Well, if you observe the reaction carefully, it says we have got an alkene to which we added X2, generally in presence of non-polar solvents such as CCl4, which results in the formation of vicinal dihalide. However, one very important feature that you guys will have to remember is that this addition of halogen across carbon-carbon double bond is an anti-addition. Okay, so let's see here. Suppose if I have some alkene, carbon-carbon double bond, and representing its precise three-dimensional structure, two bonds coming outside the plane of paper, two going inside the plane of paper. Okay, to which you are adding X2 in presence of non-polar solvents. Guys, see here. Well, everyone, now, ideally speaking, this both being identical atom, the electron density will be symmetrically distributed between the two atoms such that there will be no polarization of a bond, which is correct. However, there exists something called as instantaneous dipole moment. What is instantaneous dipole moment? For some instance, because electron density is always movable, for some instance, the electron density between the two halogen atoms can shift momentarily towards one of the atom, one nucleus of one of the atoms. So let's say for some instance electron density drifted towards the other X, so that X will acquire delta minus and this halogen will acquire delta plus. The moment this becomes deficient halogen atom, it is now vulnerable to undergo attack from a nucleophile, and because we mentioned earlier alkenes are pi bonded nucleophiles, so they'll always have a tendency to attack at the deficient atom. So what happens is this pi bond will shift towards one of the carbon, making this carbon electron rich, which attack at this deficient halogen, and the other carbon become deficient, which is simultaneously attacked by the lone pair of the same halogen, and other leaves in the form of X minus. Now guys, whatever arrows I have shown, all are taking place simultaneously. There was instantaneous dipole moment developing deficiency at one of the halogen. So pi bonded alkene attacked at the halogen, other carbon became deficient, but before it could become carbocation, the lone pair of same X attacked here with a simultaneous loss of halide ion in the form of X minus. So this X got added from one of the side of carbon-carbon double bond, resulting in the formation of cyclic halonium ion, which you can show like this. and the remaining bonds. See, because this X is getting added from one of the side, these two bonds will flip little upwards. So we can show them like this. Find and the positive charge on X will ensure that it is still deficient. This is what you call it as cyclic halonium ion or bridged halonium ion also this is referred sometimes. Now if you look at this molecule, this cyclic halonium ion has got three-membered structure, three-membered ring structure, and three-membered ring have always been a strained ring, and that's why this molecule would always wants to open up by breaking any one of this carbon halogen bond. So this carbon halogen bond, this is carbon halogen bond. Because halogen being more electronegative, both the carbons will carry a delta plus charge on them. So another halide ion which left in the form of X minus is now all set to attack at this deficient carbon. So it can either attack at this delta plus carbon or at this. If it attacks here, let's call it as path A. And if it attacks at the other deficient carbon, let's call it as path B. Let's say if path A attack takes place, this bond will break. If path B attack takes place, this bond will break. So we have to consider both the probabilities to get the corresponding product. However, the point to be noted, wherever it is attacking, but the attack of X minus is taking place from the opposite side of existing halide. Of course, because this side is already blocked. So X minus is attacking from the opposite side, and this is what we said is anti-attack. Because it is anti-attack, we will call it as anti-addition. So what product are we getting? Let's see that. So let us consider this is path A attack and this is path B attack. Look, if path A attack will take place, so this X will be above the plane, this bond will break, and the other X will be below the plane. So its corresponding Sohor's projection will be X attacked from above the plane. That is X, and this two bond will flip downward, but the bond which is coming outside the plane will remain outside the plane, and the one which was inside will still remain inside the plane. Fine. And because of attack of path A, this bond have been broken. So X at other carbon is pointing downward, and this two bonds as it is. This is the Sohor's projection. Well, if path B attack takes place, meaning attacking at, let's call this is carbon 2, this is carbon 1. So attack at carbon 2 will break this CX bond. So at carbon 1, X will be pointing downward. So in the Sohor's projection, X is now pointing downward, and the remaining two bonds as it is. And because attack via path B is taking place from above the plane, here the X is above the plane, and rest two as it is. Now guys, we'll have to find out what is the relation between these two. Well, earlier when we studied isomerism, we learnt very well in detail that to find out relation between these two. Guys, what are we going to do? Can anyone answer me here in the chat box? Come on. How can we find out relation between these two? Whether they are enantiomer or whether they are mesocompound. How would you do that? Anyone? Okay. So these two can be related to each other by converting them into their corresponding Fisher's projection. Yes. But to convert them into their Fisher's projection, we will always want the group at this two carbon in a set of 2, 4. As of now, if you consider this imaginary plane, 3 are above the plane, 3 are below the plane. That's not going to work for us. We want set of 2, 4. So we'll have to do carbon-carbon rotation, bring the group in a set of 2, 4, and then see their corresponding Fisher's projection. That will help us to find out relation. Well, guys, this is the general mechanism, okay? You will observe when you carry out this reaction, whatever is the stereochemistry of starting compound, you get a specific stereochemistry of a product. So when a particular stereoisomer gives you a specific stereoisomer, we call it as a stereospecific reaction. So in this stereospecific reaction, whether starting compound is cis or trans, and whether the product obtained is racemic mixture or meso compound. To find out that, we can simply apply the trick. So let me share one simple trick to find out the product directly in the Fisher's projection. So guys, let's say the question which was asked here, you can see 2017 question. The number of stereoisomers obtained by the bromination of trans to butene. Okay. Well, everybody here. Simple trick which I want you all to remember is this. Look, whenever I say syn cis or same, okay, you will treat it as plus. Just a trick. Whenever I say trans, anti, opposite, I'll say minus. Let's put this in a cloud. This is the important thing for us to apply the trick. Cis, syn and same. Everyone pay attention to what I'm saying, okay? Whenever I'll be using term cis, syn or same, meaning I'll treat it as plus. Whenever I'll say trans, anti and anti or opposite, I'll call it as minus. Now basic rules of mathematics we all are aware. Plus plus is plus. Plus minus minus. Minus plus is again minus. Minus minus is plus, right? So those things we are going to apply here. What is that? Look, suppose if I have been asked to find out a product of question. Addition of bromine to cis to butene. So let's say I've got cis to butene. Guys, listen to me carefully. Cis to butene, and to which I'm adding, let's say bromine. In presence of non-polar solvent. Okay, what is going to be a product? Well, like I said, it is always easier for us to find out the product obtained provided we are able to compare the structures in the Fisher's projection. So how are we able to put the structure directly into Fisher's projection is what I'm teaching you. Make sure that you're paying attention to it. So we know the fact the starting compound that we have taken is cis. Okay, I'll write it down. This is cis. Addition of bromine to an alkene in presence of non-polar solvent is always anti-addition. Okay, so guys, tell me, when it is cis or cis, syn or same, you call it plus. So this is plus. But we know that addition of halogen in presence of non-polar solvent is anti-addition. Anti meaning it is minus. So what is going to be the stereochemistry of product? Look, when you add bromine, unsaturated compound becomes saturated, right? And how many carbon you get? 1, 2, 3, 4. So I'll be getting compound containing 4 carbon. I'll be getting compound containing 4 carbon like this. Whereas first and the last carbon is methyl. So I will always put that first. Unsaturated compound will become saturated. Okay. But now the newly added atoms are going to be 2 bromine, which I have to add at carbon number 2 and 3. I have to add at carbon number 2 and 3. But where should I add it? Should I add it on the same side or on the opposite side? So where to add will be answered by this simple mathematic. Plus and minus is minus. Plus and minus is minus. Minus meaning opposite. So the 2 newly added bromine should be added on the opposite side at carbon number 2 and 3. So if I'm putting 1 bromine at carbon number to the right, then other bromine at carbon number 3 to be put at the left. And of course remaining valencies are these 2 H's. So let's put them here. Well, but I made a choice of putting bromine at carbon number 2 to the right and bromine at carbon number 3 to the left. But other possibility is I could have put bromine at carbon number 2 to the left and bromine at carbon number 3 to the right, because if you remember, both path A and path were possible. Path A and path B both were possible. So again, first carbon and the last carbon, you made it methyl. Now plus minus is minus, minus meaning opposite. So the two newly added bromine has to be put opposite side in the fissure. So at carbon number 2, earlier you put it to the right, now I'll put it to the left. At 3, I put it to the left, so here I can also put it to the right. So these are the two possibilities. So guys, these are going to be your two structures. What is the relation here? Well, this is a chiral carbon atom, even this is a chiral carbon atom. Two chiral carbon, but there is no mirror plane of symmetry. Is this plane dividing molecule into two equal half? See, upper part and lower part, are these mirror images? No, they are not. So there is no mirror plane of symmetry, meaning this is optically active isomer of 2,3-dibromobutane. Similarly here, this is a chiral carbon and a chiral carbon, no mirror plane of symmetry, so optically active. So even this is optically active isomer of again same compound 2,3-dibromobutane. But if you relate these two, you will see these two are optically active isomer of the same compound, which are related to each other as a mirror images, which means they are nothing but racemic mixture, because I said the attack of X minus takes place at the carbon with the equal probability, which means this both will be obtained in equal amounts. So the product is racemic mixture. So you see, a particular stereoisomer gave you a specific stereoisomer, that is dextro and levo of 2,3-dibromobutane. Hence you call it a stereospecific reaction. So guys, this simple trick helps us to get the product straight away without even referring to the mechanism. Are you understanding, everyone, this trick? Yes. Okay. So let's now try to solve the question. Question was right here. The number of stereoisomers obtained by the bromination of trans to butene. If I apply the same question to this reaction, find out the number of stereoisomer by addition of bromine to cis to butene, then answer would have been what? 2. That is cis, that is capital R and capital S, meaning dextro and levo, let's say. Now we have to apply that to trans. Let's do it with trans. Shall we do it trans here itself? Chalo, let's do that here. Now instead of cis, they are saying trans. Okay. So HC CH3 double bond C, that's methyl. And this is hydrogen atom. And you're adding bromine in presence of TCl4. Well, some important information, this is trans. Addition of bromine in presence of non-polar solvent is always going to be an anti-addition. So trans is minus. Okay, this time it is minus. Anti-addition is also minus. Minus is plus. Plus meaning same. Meaning the two newly added bromines are going to be on the same side in the Fischer's position. Either you put both to the right or you put both to the left, which means the product obtained would be. See, first, second, third, fourth. So first and the fourth carbon is methyl by default. Minus is plus. Plus meaning same. So both the bromine to be added on the same side in the Fischer. So either you should put both bromine to the right. Remaining will become H, or methyl and methyl, bromine and bromine, right? Both either to the right or to the left, and H and H. What is the relation, everyone? Well, sometimes students look at it like this. Chiral carbon and chiral carbon, optically active. Chiral carbon, optically active, and both are mirror images. No. Why no? because this is chiral, even this is chiral, but there is a mirror plane of symmetry. If I pass imaginary plane like this, it is dividing molecule into two equal half. And when compound has two chiral carbon and having mirror plane of symmetry, it is optically inactive. Such compound is what you refer it as meso. So whether this or this, both are identical. Imagine if I hold this two terminal and rotate is 180 degree, either clockwise or anti-clockwise, keeping them in same plane. So this molecule is going to be exactly this, right? If I rotate it like this. Understanding? So in that case, I will say that this molecule which you have obtained is one and the same thing. So both are nothing but meso only. So I will say the product obtained is just one isomer which is meso. Here you had two isomer. One was, what do you say, capital R or enantiomers rather, and this is just a meso. So the question was the number of stereoisomer obtained by bromination of trans to butene. So bromination of trans to butene is producing only one compound, that is meso. Hence your right answer is option A. Guys, did you all get it? Everyone? Well, Arun, we would have loved to take a chapters like Amin as you are asking. We appreciate that, but then due to lack of time, due to the time limitations, we aren't able to continue. So my dear students, in this today's complete organic chemistry in one shot, we have covered some important chapters like general organic chemistry. We talked about isomerism, we covered reaction mechanism, we saw some reaction of alkyl halide, we saw some reaction of hydrocarbons as well. Of course, we would have loved to continue and take more chapters and more concepts, but due to limitation of time, we are unable to do it. So we'll have to stop here today, keeping the time frame of this session in mind. But it was amazing time with you guys. So I wish you all the best to all those who are appearing for this weekend's NEET examination, and also all my best wishes to all of them, those who are appearing for JEE advanced examination in the month of August. So guys, that is it from our today's class. I'll see you soon in the upcoming classes. Stay tuned with Physics Wallah. Thank you so much, everyone.